Hello there, and a very warm welcome to Science for Sleep. I am truly, deeply glad that you have decided to join me here tonight. Before we begin our journey, take a gentle moment to settle in and make yourself completely comfortable. Perhaps you are already lying down, feeling the soft weight of the evening settle over you. Perhaps you are sitting quietly in a peaceful corner of your room. Or maybe this video is simply playing softly in the background, a gentle companion as you slowly wind down after a long, busy day. However you have arrived here tonight, please know that you are in exactly the right place. Science for Sleep is dedicated entirely to exploring grand, breathtaking ideas in the calmest and most gentle way imaginable. There is absolutely no rush here, and no pressure whatsoever to keep up with every single detail. It is simply a slow, winding journey through the realms of science, curiosity, and the infinite universe, beautifully designed to help your mind softly relax while it learns something wonderful and new. Tonight, we are going to gently explore a question that sounds deceptively simple at first. How big, in truth, is TON 618? Now, if you have never heard the name TON 618 before, please know that is completely okay. Even among the grand array of astronomical wonders, it is not something that typically comes up in our everyday waking conversations. But once you begin to learn about it, it quickly and beautifully becomes one of those cosmic marvels that quietly, permanently reshapes the very way you perceive the universe. Because TON 618 is not merely large. It is not even just extremely large. It is, in fact, one of the absolute largest black holes humanity has ever discovered. And when astronomers and scientists try to describe its unfathomable size, they almost always run into a very strange, humbling problem. The numbers are so unimaginably enormous that our human brains struggle to attach any real, tangible meaning to them. We can easily write the numbers down on paper. We can speak them out loud into the quiet air. But actually, truly imagining what those vast symbols represent is another matter entirely. That is precisely what we are going to gently explore together tonight. Not quickly, and certainly not with complicated mathematics or dry, technical jargon. Instead, we will drift along slowly, step by gentle step, gradually painting a mental picture of just how incredibly, breathtakingly enormous this celestial object truly is. But before we dive into the deep, quiet waters of this cosmic scale, let me pause to ask you something wonderfully simple. Where are you listening from tonight? Perhaps you are at home, nestled in some quiet, familiar corner. Maybe the lights around you are already turned off, leaving only the soft shadows. Perhaps you are cozily curled up under a warm, heavy blanket. Or maybe this video is just playing softly on a phone resting on the nightstand beside your bed. Wherever you happen to be in the world tonight, it is incredibly beautiful to remember that while you are listening to my voice, the vast universe far above you is quietly, endlessly continuing its grand and intricate story. Deep in the dark, new stars are gently forming. Entire galaxies are drifting silently through the cosmic ocean of space. And far, far beyond the reach of even the most powerful telescopes you could ever imagine looking through with your own eyes, TON 618 sits in the deepest, most distant parts of the cosmos, doing what black holes do best, gently pulling, consuming, and elegantly shaping the very fabric of space around it. If you feel like sharing a piece of your world, you can always leave a quiet comment below about where you are listening from tonight. It is always so wonderfully heartwarming to see how far these quiet science journeys travel across our beautiful planet. And if you find these kinds of slow, peaceful explorations soothing to your soul, you can also like the video and subscribe to our channel. That simple act helps more weary minds discover science for sleep, and it allows us to keep crafting these calm, soothing science stories just like this one. All right, now that we are completely settled in and cozy, let us begin our journey with a very simple, quiet thought. Most of us already have a basic, intuitive idea of what a black hole is. Even if you have never formally studied the wonders of astronomy, you have undoubtedly heard that mysterious phrase before. Black holes appear in movies, captivating documentaries, and science books all the time. They have easily become some of the most famous and intriguing objects in the entire known universe. Usually, they are described in a way that sounds delightfully mysterious and a little awe-inspiring. They are spoken of as places where gravity reigns so supreme, so incredibly strong that absolutely nothing can escape its grasp, not even light itself. And that classic description is actually remarkably accurate. A black hole forms when an unimaginably vast amount of matter is tightly squeezed into an incredibly, almost impossibly small region of space. When so much mass is packed together in such a concentrated way, gravity becomes overwhelmingly intense. If anything wanders just a little too close, it can no longer find a way to escape that powerful, silent gravitational pull. There exists a definite boundary wrapped around a black hole, known poetically as the event horizon. Once any object crosses that invisible, silent boundary, there is simply no coming back. But here is something that might surprise you. Black holes are not all cast in the same mold. In truth, they exist in a breathtakingly wide range of sizes. They span from the relatively small ones, born from the dramatic collapse of dying stars, to the truly colossal monsters that sit quietly in the absolute centers of distant galaxies. For instance, when a massive star finally runs out of its nuclear fuel and collapses under its own immense weight at the end of its life, it can leave behind a stellar black hole that weighs perhaps 10 times the mass of our own sun. To our minds, that might already sound unimaginably huge, and indeed, in its own quiet way, it is. Compressing the staggering mass of 10 entire suns into a tight, dark region only a few dozen kilometers across is a truly astonishing cosmic feat. Yet, when compared to the true giants of the deep universe, those stellar black holes are actually quite modest, almost humble in scale. At the dark heart of most galaxies, including our very own Milky Way, astronomers have discovered something vastly larger. These cosmic giants are known as supermassive black holes. The one residing at the center of our galaxy is known as Sagittarius A star. Its immense mass is estimated to be about 4 million times that of our Sun. That number by itself is already incredibly difficult for the human mind to picture. 4 million suns all gathered in one place. And yet, even this enormous, staggering object turns out to be relatively small when compared to the sheer scale of Ton 618. This is because Ton 618 belongs to an even more extreme, almost terrifying category. It is what astronomers sometimes call an ultra-massive black hole. Its mass is so unimaginably vast that when scientists first calculated its true dimensions, the resulting figure seemed almost impossible to believe. Ton 618 is estimated to contain an astonishing 66 billion times the mass of our Sun. 66 billion. Just whispering that number out loud feels a little strange, almost surreal. Our human brains are quite comfortable dealing with familiar numbers like 10, 100, or perhaps even 1,000. But once we venture into the realm of billions, the scale becomes slippery, sliding away from our grasp. Consider this: a billion seconds lasts for more than 30 long years, and a billion minutes stretches over 1900 years. So, when we say that TON 618 contains 66 billion suns worth of mass, we are stepping onto a stage that stretches far beyond any ordinary human experience. Yet, this is precisely where the cosmic story becomes even more fascinating. When people hear the word mass, they often imagine a physical weight, something heavy, solid, and incredibly dense. However, the true physical size of a black hole is not merely about how heavy it is. It is also about how wide its mysterious event horizon becomes. For a cosmic giant harboring tens of billions of solar masses, that event horizon expands to a truly breathtaking size. It grows large enough, in fact, to swallow our entire solar system many times over. We will gently explore that physical comparison a little later, as it turns out to be one of the easiest ways to truly visualize this gargantuan scale. For now, let us keep just one simple idea in mind. Ton 618 is not merely a little bigger than other black holes. It is operating on an entirely different cosmic level. To understand how scientists managed to discover something this impossibly large, we must step back for a moment and reflect on how astronomers actually study objects that lie so incredibly far away in the dark. After all, no human has ever visited a black hole. We cannot send a spacecraft to hover safely nearby and take photographs. Even the nearest black holes lie far beyond the reach of our current technology. Instead, astronomers must rely entirely on light. Telescopes quietly collect tiny, precious amounts of light that have traveled across the vast emptiness of the universe for millions, or even billions of years. By analyzing that ancient light with great care, scientists can learn a surprising amount about these distant objects. They can measure how quickly something is moving, estimate its temperature, and even calculate exactly how much hidden mass must be present. Ton 618 was discovered through this very kind of patient, meticulous observation. At first, it did not appear to be a black hole at all. What astronomers actually saw was a brilliant beacon known as a quasar. Quasars are easily among the brightest, most luminous objects in the entire universe. They shine with an absolutely dazzling intensity, often completely outshining the vast galaxy that surrounds them. That brilliant brightness does not come from the dark black hole itself, of course, because black holes emit no light of their own. Despite these vast differences, both black holes strictly obey the very same fundamental laws of gravity. Their extraordinary behavior is beautifully described by the theory of general relativity, masterfully developed by Albert Einstein. According to this profound theory, massive objects elegantly curve the very fabric of spacetime around them. The greater and more concentrated the mass, the deeper this invisible curvature becomes. Black holes, indeed, represent the most extreme and breathtaking example of this cosmic warping. At the absolute boundary of the event horizon, the curvature becomes so overwhelmingly strong that every possible path in existence leads inevitably inward. This underlying, majestic principle remains entirely the same, whether the black hole contains a modest few times the mass of our own sun or tens of billions. What changes so dramatically is the sheer, unimaginable scale. Sagittarius, a star, bends the fabric of spacetime strongly within a tight region smaller than Mercury's orbit. In contrast, N618 bends spacetime across a colossal region far larger than our entire solar system. Instead, it is generated by the superheated matter swirling furiously around the black hole, gas and dust falling. Another deeply surprising consequence of this vast difference in scale involves the relentless pull of tidal forces. Near smaller, more compact black holes, these tidal forces grow astronomically strong as any object approaches the threshold of the event horizon. The sheer difference in gravity between the front and back of an object can violently stretch it apart. Near ultramassive giants like T618, however, the event horizon lies so incredibly far from the central singularity that the tidal forces at this fateful boundary can remain relatively mild. In theory, a daring spacecraft crossing the event horizon of T618 might not feel any dramatic, destructive stretching immediately. This strange, counterintuitive effect beautifully illustrates how scale radically alters the experienced nature of these black holes. The larger a black hole becomes, the gentler the threshold of its event horizon may locally appear, even though any hope of escape remains utterly impossible once it is crossed. Gazing upon these two cosmic objects side by side, the quiet, slumbering black hole nestled in our own home galaxy and the distant, roaring giant powering Ton 618, offers a profoundly useful perspective on just how incredibly varied black holes can be. Both obey the same eternal physical laws. Both warp the fabric of spacetime around them. Toward a black hole do not simply drop straight in immediately. Both possess a silent event horizon beyond which absolutely nothing returns. Yet, their physical sizes, radiant brightness, and surrounding environments can differ almost unimaginably. Sagittarius, a star, represents the common, quiet kind of black hole found resting in many mature galaxies today, massive, yet relatively calm and dormant. Conversely, N618 vividly demonstrates what can happen when a black hole swells to an extraordinary, mind-boggling mass while actively and voraciously feeding on the rich surrounding matter. It transforms into one of the brightest, most dazzling objects in the entire known universe. Galaxies often appear serene and calm when viewed from a great distance. Through the lens of a telescope, a distant galaxy might look like a graceful, luminous spiral of stars slowly and silently turning through the emptiness of space. Billions of suns shine in perfect harmony, forming glowing, majestic arms that stretch across tens of thousands of light years. Ethereal clouds of cosmic gas drift quietly between those stars, occasionally collapsing under their own weight to give birth to new generations of stellar systems. From far, far away, the entire grand structure can seem peaceful, harmonious, and orderly. Instead, they gracefully spiral inward, gradually forming a colossal, spinning structure known as an accretion disk. Yet, hidden deep within the heart of many of these galaxies lies something far more powerful, a force of nature. At their very centers sits a monstrous black hole. Not a small stellar mass remnant formed from the quiet collapse of a single star, but a massive, eternal gravitational anchor containing millions or even billions of times the mass of our Sun. These central black holes are so common that modern astronomers now firmly believe nearly every majestic, large galaxy hosts one at its very heart. Our own spiral home, the Milky Way, is a perfect example of this celestial rule, harboring a silent central black hole known as Sagittarius, a star. As we discussed earlier, this dark, invisible object holds an immense mass equivalent to about 4 million of our suns. Yet, it quietly and gracefully influences the orbital motions of the ancient stars residing in the innermost sanctuary of the galaxy, even though it occupies only a vanishingly tiny portion of cosmic space compared to the sprawling expanse of the galaxy itself. For a very long period, astronomers remained deeply unsure whether this grand celestial arrangement was merely a rare, unusual anomaly. As this cosmic material spirals closer and closer to the precipice, it heats up dramatically and violently. Perhaps our Milky Way simply happened to contain a central black hole by chance, while other distant galaxies remained entirely devoid of them. However, as our telescopes grew vastly more powerful and more precise observations were meticulously gathered, a clear, undeniable pattern began to beautifully emerge. Large galaxies almost always host a supermassive black hole at their very core. Some of these gravitational giants are relatively modest by vast cosmic standards, containing only a few million solar masses. Others, however, grow unimaginably larger, easily reaching several billions of solar masses. And in extremely rare, awe-inspiring cases, the central black hole can grow so profoundly massive that it becomes one of the single most monstrous objects in the entire observable universe. The colossal giant powering to 618 belongs to this extreme, mind-bending category. To truly understand why galaxies contain these enormously powerful objects, it helps to reflect deeply on how galaxies themselves initially form and continuously evolve. In the ancient infant universe, vast, primordial clouds of gas gradually collapsed under the relentless pull of gravity to form the very first nascent galaxies. Deep inside those growing cosmic structures, brilliant stars began forming in truly enormous numbers. Temperatures within these swirling disks can reach unthinkable millions of degrees. As these young galaxies slowly evolved over eons, some of their cold gas sank steadily toward the center, pulled inward by the insatiable grip of gravity. At the same time, smaller, neighboring galaxies frequently collided and seamlessly merged with one another in a dramatic, slow-motion cosmic dance. When two such galaxies merge, their central black holes can eventually drift toward the center of the newly combined system. Over vast stretches of cosmic time, these central black holes may merge as well, creating an even more formidable giant. This epic process repeats endlessly over billions of years. Gas falls helplessly inward. Stars quietly orbit the center. Galaxies collide and gracefully merge. Black holes grow larger and larger, expanding their dark horizons as they continuously absorb surrounding matter and merge with other black holes. Through these turbulent, ancient processes, the central regions of giant galaxies become the permanent home to extremely massive black holes. At those extreme temperatures, the superheated gas begins to glow intensely, producing truly enormous amounts of brilliant radiation. One of the most profoundly interesting discoveries in modern astronomy is that the total mass of a galaxy's central black hole appears to be directly related to the overall mass of the host galaxy itself. This remarkable cosmic relationship is known to science as the M-sigma relation. In simpler terms, galaxies that possess larger central stellar bulges tend to contain significantly more massive black holes. The countless stars in those dense bulges move much faster under the powerful influence of the galaxy's gravity, and those rapid stellar motions correlate incredibly closely with the mass of the central black hole. This strongly suggests a beautiful coevolution, showing that galaxies and their central black holes grow together in perfect harmony. Even though the dark black hole occupies only a vanishingly tiny fraction of the galaxy's total physical volume, its gravitational and energetic influence can extend across vast, unimaginable distances. When a black hole actively and violently consumes gas, the intense energy released in the surrounding, glowing accretion disk can heat or forcefully expel gas throughout the entire galaxy. This dramatic process may ultimately slow down the birth of new stars by violently pushing the vital star-forming gas outward. Astronomers refer to this powerful, self-limiting phenomenon as feedback. As the black hole ravenously feeds on nearby matter, it releases an enormous, brilliant torrent of energy in the process. This shimmering, glowing disk is precisely what astronomers observe from across the unimaginable vastness of the universe. That released energy profoundly affects the surrounding host galaxy, which in turn directly influences how much raw material can continue falling helplessly toward the black hole. In this delicate, reciprocal way, the galaxy and the central black hole carefully regulate each other's growth. For most mature galaxies today, this intense cosmic interaction has become relatively quiet and peaceful. The central black holes remain firmly in place, but they no longer actively consume such large amounts of gas. Their surrounding stellar regions have stabilized, and the galaxies now evolve much more slowly and gracefully. But in the wild, early universe, things were very different. Young, turbulent galaxies contained much larger, richer supplies of gas, and violent collisions between galaxies occurred far more frequently. These turbulent conditions allowed central black holes to grow with astonishing rapidity, fueling the creation of extremely bright, majestic quasars. T618 appears to be one of the most breathtaking and dramatic examples of such an primordial system. And in the singular case of T618, the spectacular quasar it produces is almost unbelievably bright. Its colossal central black hole has slowly grown to encompass tens of billions of solar masses, rightfully placing it among the largest, most formidable black holes ever observed by humanity. Around this invisible titan, truly enormous amounts of swirling gas form a brilliant, feverish accretion disk that shines with an almost incredible, blinding luminosity. This magnificent quasar releases such a staggering amount of energy that it can easily outshine the entire host galaxy surrounding it. That single, astonishing fact alone reveals something profoundly remarkable. Normally, the gentle light emanating from billions of stars dominates the overall appearance of a galaxy. Yet, in systems like T618, the central black hole defies this norm, transforming into the brightest, most radiant object by far. The surrounding galaxy becomes almost secondary, a mere whisper compared to the blazing quasar at its ancient core. Even though the black hole itself remains completely invisible, cloaked in absolute darkness, its immense presence profoundly shapes the entire central region of the galaxy. Vast streams of gas flow continuously inward toward the churning accretion disk, while intense, blinding radiation pours endlessly outward into the cold vacuum of space. At the same time, fierce jets of highly energetic particles may shoot violently away from the magnetic poles of the black hole, traveling across enormous, mind-boggling distances. It shines so intensely that its ancient light can be clearly detected from billions of light-years away. Amazingly, all of this chaotic activity occurs within a local region that represents only a tiny, microscopic fraction of the galaxy's total vast size. This stark contrast between physical scale and cosmic influence remains one of the most fascinating and mysterious aspects of supermassive black holes. A grand galaxy might span over 100,000 light-years across, while the dark event horizon of its central black hole might measure only a few billion kilometers in diameter. And yet, the unimaginable energy released near that relatively tiny boundary can profoundly influence the destiny of the entire galaxy. T618 pushes this terrifying idea to its absolute extreme. Its central black hole is so unimaginably massive that the dark event horizon alone would effortlessly swallow our entire solar system if it were placed at its center. The fiercely glowing accretion disk surrounding it likely spans vast distances comparable to whole planetary systems, or perhaps even larger. And yet, All of this cosmic drama exists within a lonely galaxy located billions of light-years away from our own. Astronomers who spend their lives studying such distant objects often describe them, with a sense of quiet awe, as ancient monsters slumbering at the centers of giant galaxies. They are called so not because they are arbitrarily violent in a dramatic, chaotic sense, but because their sheer scale and immense power stretch far beyond anything ever found in our ordinary stellar systems. When dedicated astronomers carefully studied the light journeying from this distant quasar, they noticed something highly unusual. Yet, remarkably, even these cosmic giants faithfully follow the very same physical rules that govern much smaller stellar mass black holes. Relentless gravity pulls matter inward. Tremendous energy is continuously released as glowing gas spirals helplessly toward the dark event horizon. And the highly disturbed surrounding environment reveals vital clues about the deeply hidden mass at the center. In the specific case of TON 618, those cosmic clues reveal one of the largest, most powerful gravitational engines ever discovered in the universe. Under normal circumstances, matter drifting silently through the vastness of space usually behaves in a fairly peaceful, predictable way. Cold gas clouds move slowly and gracefully through galaxies, sometimes gently collapsing under their own gravity to spark the birth of new stars. Tiny dust grains float quietly between those clouds, occasionally gathering into larger, more complex structures over millions of quiet years. Even when gravity begins pulling material inward, the celestial process often unfolds with a slow, majestic gradualness. Stars form over incredibly long periods of time, and planetary systems patiently assemble from rotating disks that evolve gently across vast, quiet stretches of time. The swirling gas surrounding it was moving extremely fast, far faster than what would normally and reasonably be expected under ordinary cosmic conditions. However, the extreme environment near a supermassive black hole shatters that calm, peaceful picture quite dramatically. As surrounding matter approaches the boundary of a black hole, relentless gravity begins to completely dominate every single aspect of its motion. Cold gas that might have drifted peacefully and quietly through interstellar space suddenly accelerates to extreme velocities. Orbital paths that once curved gently now spiral inward with terrifying, ever-increasing speed. The closer this doomed material moves toward the black hole, the stronger and more inescapable the gravitational pull becomes. Yet, even in this extreme environment, the process is not nearly as simple as matter falling straight down into a dark, yawning opening. Indeed, space near a massive black hole is usually incredibly crowded with swirling gas, thick dust, and intense, chaotic radiation. Instead of plunging directly and cleanly inward, the vast majority of that material begins to rapidly orbit. The beautiful, chaotic result is a flattened, rotating structure known to science as an accretion disk. Inside this highly energetic disk, matter behaves very differently indeed from the serene gas clouds drifting peacefully through the rest of. The only plausible way to explain those dizzying speeds was the formidable presence of an extraordinarily massive black hole. The galaxy. Each tiny, restless particle of gas is relentlessly pulled inward by the immense grasp of gravity, even as it desperately dances sideways around the yawning maw of the black hole. As these frantic particles interact in the crowded dark, they violently collide and rub against one another, creating a fierce, chaotic friction. This relentless friction gradually converts the raw gravitational energy of their fall into intense, searing heat. The deeper this gas spirals into the swirling depths of the accretion disk, the hotter and more volatile it inevitably becomes. Temperatures in the cooler, outer reaches of this majestic accretion disk might reach thousands of degrees. Yet, as one ventures closer to the absolute center, the temperatures climb astronomically higher, sometimes soaring to millions of degrees. At such unfathomable temperatures, the trapped gas begins to glow with an intense, haunting brilliance. Blinding radiation pours tirelessly outward across the vast electromagnetic spectrum, from soft visible light to fierce ultraviolet, and even to the most powerful invisible X-rays. It is this brilliant, escaping radiation that ultimately allows patient astronomers on Earth to detect these magnificent quasars across truly enormous cosmic distances. By meticulously analyzing the rapid motion of the gas and the brilliant brightness of the quasar, scientists were ultimately able to estimate the immense mass of the unseen object lurking at its center. The spectacular quasar surrounding T618 shines so intensely bright precisely because absolutely enormous amounts of cosmic matter are spiraling feverishly into the black hole's immense accretion disk. With every passing second, vast, unimaginable quantities of gas fall helplessly inward, releasing truly tremendous reservoirs of energy as they journey ever closer to the mysterious event horizon. Yet, the final journey of that doomed matter is far from smooth or peaceful. Deep inside the churning accretion disk, the gas whipped into a frenzy moves at extraordinary, dizzying speeds. Some of this celestial material travels at a highly significant fraction of the ultimate speed of light. At such unfathomable velocities, even the smallest, most fleeting collisions between particles can release sudden, enormous bursts of raw energy. Violent turbulence quickly becomes common and chaotic. Intricate magnetic fields twist relentlessly through the disk, vigorously stirring the superheated gas and creating powerful, sweeping currents of highly charged particles. These powerful magnetic forces can sometimes fling some of the gas completely away from the disk entirely, launching it outward into the cold void in the form of high-speed cosmic winds. Indeed, not all the matter that bravely approaches the black hole actually falls inside its dark embrace. That is precisely how they arrived at the truly astonishing figure of around 66 billion solar masses. A significant portion of it is violently blown outward, expelled long before ever reaching the threshold of the event horizon. These dramatic outflows can carry huge, sweeping amounts of energy deep into the surrounding galaxy, warming distant gas clouds, and sometimes forcefully pushing pristine material far away from the active galactic center. At the very same time, another deeply dramatic phenomenon can occur near the silent poles of the black hole. In many highly active quasars, incredibly narrow, focused beams of particles called relativistic jets erupt violently from the chaotic region close to the black hole. These spectacular jets travel outward along the black hole's own rotational axis, swiftly shooting through empty space at speeds agonizingly close to the speed of light. The exact, mysterious mechanism that launches these colossal jets is still a highly active area of scientific research, but invisible magnetic fields appear to play an absolutely crucial role. The rapidly spinning accretion disk and the dizzying rotation of the black hole itself twist these magnetic field lines into tight, highly energetic coils. These powerful magnetic structures can accelerate charged particles and channel them into narrow, focused beams that escape far into the dark, silent intergalactic space. In some distant galaxies, these majestic jets extend outward for hundreds of thousands of light years. For a quiet, distant observer, they appear as truly enormous, luminous streams of energy emerging triumphantly from the very heart of the galaxy. Even today, Ton 618 remains one of the most monstrously massive black holes we have ever known about in the cosmos. All of these frantic, violent processes, intense heating, chaotic turbulence, blinding radiation, and colossal jets, occur simultaneously in the extreme environment closely surrounding the black hole. But inevitably, some stubborn matter continues its relentless, fatal inward spiral. As the doomed gas closely approaches the absolute boundary of the event horizon, its falling speed increases dramatically and terrifyingly. The overwhelming gravitational pull becomes entirely irresistible, and the gas completely loses its ability to maintain any stable, safe orbits. At that fateful, final point, the silent matter crosses the event horizon. From the safe distance of the outside world, this profound transition is entirely impossible to observe directly. The event horizon acts as an absolute, eternal boundary where even light itself cannot escape. Any signal produced beyond that dark point is trapped forever within the deep, silent interior of the black hole. However, the dramatic behavior of matter lingering near this boundary reveals subtle hints about what must be happening within. Light emitted from the gas trapped close to the event horizon becomes stretched to much longer wavelengths due to the extraordinarily intense gravitational field. And that inevitably raises a very natural, deeply intriguing question. This haunting effect, known to us as gravitational red shift, makes the escaping light appear significantly dimmer and redder as it struggles to climb away from the black hole. To a distant observer, matter falling toward the event horizon appears to slow down with an agonizing, almost poetic gradualness. The closer it approaches that fateful boundary, the more sluggishly it seems to move through the warped fabric of spacetime. Eventually, the emitted light becomes so incredibly stretched and weakened that the descending, infalling matter softly fades from our view entirely, vanishing into the silent dark. From the quiet perspective of someone watching from the safety of the far-off cosmos, it appears as though this doomed matter never quite crosses the event horizon. Yet, the matter itself experiences a far different, much more fluid reality. From its own lonely perspective, it continues falling steadily inward, noticing no sudden or dramatic change at the precise, silent moment the event horizon is crossed. This strange, haunting difference between viewpoints arises from the most extreme and beautiful effects of gravity upon the flow of time and the journey of light. The grand theory describing these profound cosmic effects was brilliantly developed by Albert Einstein in his masterwork of general relativity. If it is indeed so incredibly massive, how big is it physically? According to that elegant theory, massive objects warp and bend the very fabric of spacetime around them. Near the edge of a black hole, this majestic curvature becomes so overwhelmingly intense that all possible paths through spacetime eventually lead inward once the event horizon is crossed. Deep inside that sacred boundary lies a dark, inaccessible region where gravity becomes truly and terrifyingly overwhelming. The exact, intimate nature of what transpires within this realm remains one of the deepest, most tantalizing mysteries in all of modern physics. At the absolute heart of a black hole, general relativity confidently predicts the existence of a singularity, a silent point where density becomes infinite and the known laws of physics break down completely. What truly occurs at that ultimate location is still entirely unknown to us. Thoughtful physicists believe that a complete, harmonious understanding of this mystery may require a new, unifying theory that seamlessly combines general relativity with the delicate principles of quantum mechanics. For the practical purposes of understanding TON 618, however, we do not need to explore the impenetrable interior of the black hole itself. Everything we can actively observe occurs safely outside the event horizon. There, the brilliant accretion disk radiates a torrent of enormous energy, while vast gas clouds orbit at almost unbelievable speeds. How wide is the quiet region where its gravity becomes absolutely impossible to escape? Powerful jets of energy and matter may blast outward into the surrounding galaxy, even as some of the drifting matter continues its final, inevitable inward journey toward that invisible boundary. Because TON 618 harbors tens of billions of solar masses, these celestial processes unfold on an incredibly grand and majestic scale. The swirling accretion disks surrounding this supermassive giant may extend across immense distances comparable to the span of entire planetary systems. Swirling gas clouds orbiting nearby move at dizzying speeds of thousands of kilometers/s, producing the distinctive, broad emission lines that astronomers observe with wonder in the distant quasar spectrum. Yet, despite the unimaginable violence of these glowing cosmic environments, the outer edge of the event horizon itself may appear surprisingly, almost poetically calm. For ultramassive black holes of this magnitude, the destructive tidal forces at that fateful boundary are relatively gentle when compared with those of much smaller, more violent black holes. The immense, sprawling size of the event horizon spreads the fierce gravitational gradient over a vastly larger distance. This means that any physical objects approaching this silent boundary might not experience violent, dramatic stretching immediately. Instead, their final, fateful plunge into the dark abyss of the black hole could occur with a quiet, serene stillness, at least at first. The true, turbulent drama unfolds only much deeper inside, forever shrouded in mystery and hidden away from the rest of the outside universe. In other words, what would the mysterious event horizon actually look like if our eyes could somehow see it? All of these energetic behaviors, the searing heating, the brilliant radiation, the powerful jets, and the final, sweeping inward fall of matter, combine to create the radiant quasar we observe from Earth. That dazzling brightness tells astronomers that to N618 is still actively, voraciously feeding. Ancient gas continues to fall steadily inward, allowing the black hole to grow ever larger over the vast epochs of cosmic time. And this realization inevitably raises another deeply fascinating, quiet question. How did a black hole ever manage to grow to such an extraordinary, mind-bending size in the first place? Drifting gas wandering lazily through a galaxy does not usually fall in a straight, direct line into a black hole. Even though gravity pulls relentlessly toward the deep center, most cosmic matter in space carries some sideways, momentum-driven motion. Billowing clouds of gas rotate gracefully as their host galaxies spin, stars orbit in eternal dances around the galactic center, and fine dust grains travel along curved, elegant paths shaped by gravity and past cosmic interactions. Because of this persistent, spinning motion, when gas finally begins to move toward a black hole, it rarely plunges directly inward in a direct line. Instead, the material begins to circle. Truly answering that profound question requires us to think deeply and carefully about scale. Around the black hole, caught in an eternal cosmic dance. As more and more gas gradually accumulates in this turbulent region, it gently flattens and shapes itself into a spinning, highly structured disk known as an accretion disk. This majestic disk resembles a vast, swirling cosmic whirlpool, where doomed matter slowly spirals inward over immense stretches of time, gradually and inevitably losing its orbital energy. Deep within this swirling disk, physical conditions become unimaginably extreme. Countless particles of gas crowd tightly together, orbiting at utterly astronomical speeds, while violently and constantly colliding with one another. These ceaseless collisions generate immense, unrelenting friction, which beautifully converts kinetic motion into searing, radiant heat. The deeper the gas ventures into the glowing disk, the faster it frantically travels and the hotter it inevitably becomes. In ordinary, tranquil environments, gas drifting through the vastness of interstellar space may remain incredibly cold, resting only a few fragile degrees above absolute zero. Yet, within an accretion disk surrounding a supermassive black hole, the temperature climbs dramatically and violently. The outer, quieter regions of the disk may reach thousands of degrees. Because space, as it turns out, is remarkably good at making even the most enormous things seem desperately small. But as one ventures closer to the center, the temperature dramatically soars into the millions of degrees. At such unfathomable temperatures, matter no longer behaves like the familiar gases we know on Earth. Instead, atoms become violently ionized. Their outermost electrons are ruthlessly stripped away, leaving behind a glowing, superhot plasma of intensely charged particles. This dynamic plasma interacts powerfully with unseen magnetic fields, creating a highly turbulent environment filled with wildly swirling currents of raw energy. Consequently, the accretion disk transforms into one of the brightest, most dazzling structures in the entire universe. Intense radiation pours ceaselessly outward across a vast spectrum of light. Brilliant visible light, invisible ultraviolet radiation, penetrating X-rays, and sometimes even highly energetic gamma rays are released into the void as the gas continues its agonizingly slow inward spiral. This brilliant, blinding glow is precisely what astronomers observe when they detect a distant, ancient quasar. The enigmatic black hole itself remains completely invisible, shrouded in absolute darkness, but the surrounding disk shines with unmatched intensity due to the truly colossal gravitational energy being unleashed. The colossal quasar associated with the legendary T618 is powered by precisely this majestic process. For example, our radiant sun feels absolutely huge when we think about it from our perspective here on Earth. Vast reservoirs of gas from the surrounding host galaxy fall helplessly toward the central black hole, forming an immense, glowing accretion disk. As this gas spirals ever inward, it heats up to extraordinary, unimaginable temperatures, producing the immense, breathtaking luminosity that allows astronomers on Earth to detect the quasar from billions of light-years away. One truly remarkable and profound feature of these accretion disks is their astonishing physical efficiency. When ordinary matter falls toward a star, much of its gravitational energy is simply converted into hidden heat deep inside the star's dense interior. But when matter plunges into a black hole's dynamic accretion disk, a vastly larger fraction of that mass can be converted directly and cleanly into brilliant outward-flowing radiation. This conversion efficiency can reach an astonishing 10%. To fully grasp how incredibly significant that is, it helps to compare it with the process of nuclear fusion. Fusion, which takes place deep inside active stars, converts only a mere 0.7% of the original mass into pure energy. Even though this stellar fusion powers our own sun and countless other stars for billions of years, the efficiency of black hole accretion is incomparably higher. This means that even a relatively small, modest amount of matter falling relentlessly into a black hole can produce truly enormous, unimaginable amounts of energy. It is more than 100 times wider than our fragile planet, and it proudly contains more than 99% of the total mass in the entire solar system. The accretion disk thus becomes a grand, cosmic furnace, burning raw gravitational energy rather than relying on nuclear fuel. Within this blazing celestial furnace, matter moves along incredibly complex paths carefully shaped by gravity, friction, and powerful magnetic forces. Gas in the outermost regions of the disk orbits relatively slowly compared with the frenzied gas situated closer to the center. But as the gas gradually and steadily loses its energy through radiating light, it drifts inevitably inward. Each step inward drastically increases its orbital speed. Near the innermost regions of the disk, the rushing matter can travel at a highly significant fraction of the speed of light itself. At such extreme relativistic velocities, the fundamental physics of the disk becomes incredibly and beautifully complex. Intricate magnetic fields twist wildly through the glowing plasma, generating violent turbulence that constantly mixes the material and systematically redistributes angular momentum. This elegant process allows some gas to steadily slip inward toward its doom, while other gas is forcefully pushed outward. Without this crucial transfer of angular momentum, the gas would simply remain forever trapped in stable, unchanging orbits and would never reach the waiting grasp of the black hole. Yet, when astronomers objectively compare our sun to other giant stars, it turns out to be fairly ordinary and modest. The disk, therefore, behaves like a dynamic, constantly shifting system, with cosmic matter slowly and inexorably migrating toward the dark abyss of the event horizon over vast stretches of time. Yet, not all of this doomed matter is destined to reach the absolute finality of the black hole itself. Tremendously powerful stellar winds can violently sweep material away from the turbulent disk, carrying hot gas back into the deeper, quiet regions of the surrounding galaxy. In certain remarkable cases, these ferocious winds can become strong enough to actively disrupt the delicate formation of new stars in nearby regions, heating or completely dispersing the fragile gas clouds that would otherwise foster stellar life. The chaotic environment surrounding an accretion disk can also give rise to another truly striking and awe-inspiring phenomenon. Colossal jets of highly energetic particles occasionally erupt from the turbulent regions near the poles of the black hole. These majestic jets form incredibly narrow streams of superheated plasma, hurtling outward into the void at velocities closely approaching the absolute speed of light. They can traverse absolutely enormous distances, sometimes stretching tens of thousands of light-years deep into the vast emptiness of intergalactic space. Although the exact physical mechanism that launches these titanic jets remains a subject of intense scientific study, astronomers believe that twisting, rotating magnetic fields play a crucial and defining role. And when we compare even those giant stars to black holes, the scale shifts dramatically once again. As the black hole relentlessly spins, it violently drags the very fabric of spacetime along with it in a mesmerizing process known to physics as frame dragging. Strong magnetic fields deeply embedded in the surrounding plasma are able to tap directly into this immense rotational energy, fiercely accelerating charged particles outward along the primary axis of rotation. The grand result of this cosmic engine is a pair of breathtakingly powerful jets emerging from the central region of the host galaxy. In the rare case of extremely luminous quasars such as to 618, the sprawling accretion disk itself may extend across distances comparable to the vast scale of our entire solar system. The cooler, outer parts of this colossal disk glow brilliantly with visible and ultraviolet light, whereas the highly compressed inner regions produce searing X-rays as the swirling gas reaches its absolute highest temperatures. Because the ancient beacon of Tun 618 lies billions of light-years away from Earth, astronomers cannot directly capture an image of the disk itself. Instead, they must meticulously study the ancient light emitted from the distant quasar, carefully analyzing the subtle spectral signatures produced by the excited gas within the disk and its immediate surroundings. These delicate spectral lines eloquently reveal how fast the gas is moving, how incredibly hot it is, and exactly how much material must be flowing into the insatiable black hole. From these precise measurements, scientists can accurately estimate how rapidly this cosmic monster is growing. Even a supermassive black hole as gargantuan as Tun 618 can steadily continue to gain mass, provided that a fresh, abundant supply of gas keeps cascading into its voracious accretion disk. 2618 sits majestically at the extreme, unimaginable end of that cosmic scale. Over millions of years, this continuous, monumental feeding process allows the black hole to dramatically increase its physical size. Yet, the rapid growth of such an unimaginably enormous black hole raises a deeply intriguing and profound scientific puzzle. The universe itself is estimated to be about 13.8 billion years old. However, Tun 618 had already amassed tens of billions of solar masses when the faint light we detect today first began its lonely journey toward Earth more than 10 billion years ago. This startling timeline implies that the black hole must have grown with extreme and unprecedented rapidity during the very early history of our infant universe. Astronomers are still working tirelessly today to comprehend how such a massive anomaly could have developed so quickly. Some compelling theories suggest that the earliest primordial black holes formed from the cataclysmic collapse of extremely massive first-generation stars, thereby creating large seed black holes that were able to grow with astonishing speed by greedily consuming the surrounding primordial gas. Other innovative ideas propose that colossal clouds of pristine gas in the early universe might have collapsed directly into supermassive black holes, entirely bypassing the process of star formation altogether. Whatever the exact physical process may have been, the immense accretion disk surrounding Tun 618 undoubtedly played a vital, irreplaceable role in its dramatic growth. Its dark event horizon stretches silently across a region of space so unimaginably wide that if it suddenly replaced the Sun at the very center of our solar system, the disk functions simultaneously as a highly efficient feeding mechanism and a stupendous energy source, allowing matter to spiral slowly inward while releasing vast, unimaginable amounts of radiation into the cold cosmos. Without that blazing cosmic furnace tightly enveloping the black hole, the quasar would never have shone with such brilliant intensity, and modern astronomers might never have noticed this truly extraordinary celestial object at all. Ultimately, understanding how any entity becomes so extraordinarily large often begins with a remarkably simple, fundamental question. Where did it all start? Every single object in this vast universe, whether it is a quiet planet, a burning star, a grand galaxy, or a silent, voracious black hole, has a humble beginning somewhere in time. Even the most colossal, awe-inspiring structures in the cosmos did not magically appear in an instant at their fully realized size. Instead, they grew gradually and beautifully over immense epochs of time, slowly shaped by the invisible, persistent hands of gravity, collisions, and the wonderfully slow, majestic movement of matter across vast cosmic distances. This universal truth is also deeply true for the monstrous black hole that powers the brilliant quasar known as N618. Today, modern astronomers estimate that the unfathomable mass of this gargantuan object is around 66 billion times the mass of our own Sun. That truly staggering number instantly places it among the largest black holes ever measured. The silent boundary of no return would extend far beyond the distant orbits of many planets. But the young universe did not begin its journey with black holes of such terrifying magnitude. When the first stars and galaxies slowly formed, black holes were much smaller, humble seeds in a vast, dark expanse. The profound puzzle astronomers now face is understanding how something could possibly grow from those modest, whisper-like beginnings into an object as incredibly enormous as to 618, especially within the relatively limited, Fleeting time available in the early universe. To deeply explore that haunting question, we must step back and consider the wild, volatile environment of the young cosmos. Our universe is currently about 13.8 billion years old. To our mortal minds, that sounds like an immense, almost eternal span of time, and in many ways it truly is. However, when astronomers observe the distant brilliance of T618, they are seeing it as it appeared more than 10 billion years ago, frozen in the deep past. The ancient light from this powerful quasar began its long journey toward Earth when the universe itself was only a mere few billion years old. This means, astonishingly, that the black hole had already reached its gargantuan mass relatively early in cosmic history. But before we venture into those grand comparisons in close detail, it greatly helps to take a quiet moment to consider something else entirely. In other words, the legendary T618 did not have the luxury of the full 13.8 billion years to slowly grow. It had far, far less time than that. How, then, did it become so massive in such a brief cosmic moment? In search of answers, astronomers have developed several elegant ideas to explain the rapid growth of these supermassive black holes. These theories involve two key, essential ingredients: the initial size of the original seed black hole, and the rate at which it can accumulate and gain new matter. Let us begin with the first vital ingredient. Every supermassive black hole must inevitably start its life as a much smaller, humble seed black hole. One intriguing possibility is that these primordial seeds formed directly from the cataclysmic deaths of very massive early stars. In the quiet dawn of the early universe, the first generation of stars, sometimes referred to as population 3 stars, may have been vastly larger and more luminous than most stars we observe today. These ancient stars formed from the pristine, untouched hydrogen and helium left behind in the immediate wake of the Big Bang. Our human brains are not naturally designed to easily comprehend these vast cosmic distances. Without heavier chemical elements to cool the collapsing gas clouds efficiently, these primitive stars were able to grow to absolutely extraordinary sizes. Some of these celestial giants may have contained hundreds of times the immense mass of our own Sun. When such colossal stars inevitably reached the dramatic end of their lives, they likely collapsed inward under their own massive gravity, forming dark black holes possessing tens or perhaps hundreds of solar masses. These dark remnants would have served as the perfect initial seeds. However, even starting with a seed black hole of a few hundred solar masses, there still remains an incredibly long journey toward becoming something as massive as T618. To successfully grow into a dark titan containing tens of billions of solar masses, the object would need to accumulate truly enormous amounts of surrounding matter. This naturally leads us to the second essential ingredient: the relentless process of accretion. Black holes grow primarily by greedily consuming the gas, dust, and other stray material from their immediate surroundings. As we discussed earlier, this doomed material forms a swirling accretion disk around the black hole, gradually spiraling inward toward the point of no return. This violent process releases an absolutely enormous amount of energy, which is precisely why these active, feeding black holes shine so brilliantly across the dark void as magnificent quasars. We originally evolved to think about earthly things like walking distances, majestic mountains, winding rivers, and perhaps the grand size of our bustling cities. But this cosmic feast of accretion cannot continue at an unlimited, unchecked rate. There exists a strict natural limit known to science as the Eddington limit. This delicate limit naturally arises because the intense radiation produced by the swirling accretion disk exerts a powerful outward pressure on the surrounding gas. If the black hole attempts to consume this matter too quickly, the ferocious outward pressure from its own brilliant radiation can violently blow that gas away before it ever falls inward. In other words, the black hole's own blinding brightness acts as a natural brake, slowing down its frantic feeding process. At this critical Eddington limit, the fierce outward pressure of the light perfectly balances the relentless inward pull of gravity. This delicate balance ultimately determines the absolute maximum rate at which a black hole can steadily grow through continuous, stable accretion. Yet, even at that maximum theoretical rate, the slow, laborious growth of a black hole requires immense spans of time. If a black hole grows continuously and perfectly at the Eddington limit, its mass doubles. roughly every 45 million years. Even the sheer scale of the Earth itself can be remarkably difficult for us to fully appreciate in its entirety. To our fleeting human minds, such a span may sound remarkably swift, yet when commencing from a modest, humble stellar seed, attaining the staggering scale of tens of billions of solar masses would still demand an immense number of these doubling cycles. It is precisely this slow mathematical reality that makes Ton 618 such a profound and mesmerizing puzzle for astronomers. This celestial titan appears to have grown with astonishing, almost impossible rapidity during the misty dawn of the early universe. One compelling explanation whispers of a cosmic shortcut. Perhaps the primordial seed black hole was already vastly larger than the typical remnants left behind by dying, ordinary stars. Rather than slowly coalescing from the quiet collapse of a single star, it might have emerged through an exotic, dramatic process known as direct collapse. In this majestic scenario, a colossal, swirling cloud of pristine primordial gas collapses directly under its own immense gravity into a black hole, altogether bypassing the intermediate stage of star formation. If this cosmic cloud were grand enough, perhaps cradling hundreds of thousands of solar masses, the newborn black hole would begin its life already far more massive than any seed born from ordinary stellar death. Starting its journey from such a giant stepping stone would make it far easier to eventually scale the steep heights of the colossal mass we observe today in 618. Another captivating possibility lies in the violent dance of ancient galaxy mergers. Once we start talking about celestial objects that span billions of kilometers, or titanic masses that exceed billions of suns, we are entering a strange realm where our basic human intuition becomes completely unreliable. In the chaotic infancy of the early universe, young galaxies frequently collided, intimately tangling and merging with one another in the dark. When two such star systems slowly unite, their central black holes must eventually spiral inward toward each other, performing a gravitational waltz before finally combining into a single, much grander black hole. This cosmic union directly unites the masses of both titans into one. Over billions of slowly unfolding years, these repeated, monumental mergers could gradually construct the ultramassive black holes that rest silently at the hearts of today's largest galaxies. Furthermore, the chaotic gas flows violently triggered by these galactic collisions could feed the central black hole far more efficiently, allowing it to gorge itself and grow at an accelerated pace. Ton 618 itself may have gone through several such frantic growth phases. Incalculable torrents of cold gas would have been forcefully funneled toward the deepest heart of its host galaxy, intensely fueling the swirling accretion disk and brightly powering the dazzling quasar we marvel at today. Each distinct epoch of intense, voracious feeding would systematically increase the black hole's gravity, and over vast stretches of time, these consecutive feeding frenzies would inevitably propel the black hole into the realm of the truly ultramassive. Yet another vital factor that likely nurtured this rapid, ancient growth was the sheer abundance and density of gas in the primordial universe. That is exactly why astronomers must often rely on evocative comparisons. These young, nascent galaxies often harbored far more raw, unblemished gas than the mature galaxies of our modern era. While this abundant gas served as the fertile nursery for brilliant star formation, it also acted as a plentiful feast for hungry central black holes. If a black hole sits comfortably in the heart of such a dense, unending supply of cosmic fuel, it can feed continuously and undisturbed for immense epochs of time. In such an enriched environment, a black hole's mass could swell dramatically over a mere few 100 million years. The fiercely glowing accretion disk currently surrounding 2618 strongly suggests that it remains an active, voracious feeder even today, or, at the very least, it was still feeding in the unimaginably distant past when the ancient light we now observe first began its long journey from that brilliant quasar. As gas continues to spiral inexorably inward, it releases an unthinkable amount of raw energy, allowing the dark behemoth to steadily accumulate even more mass. Over long cosmic epochs, however, this intense feeding process must eventually begin to slow down. As the growing black hole becomes more massive and radiates increasingly blinding energy, the fierce outward pressure of radiation from its own accretion disk can violently push the surrounding reservoir of gas away. Eventually, the once plentiful supply of nearby matter becomes completely depleted. They take something deeply familiar, like our own orderly solar system, and carefully place it next to something utterly unfamiliar and alien, like to 618. When that quiet moment arrives, the brilliant quasar slowly begins to fade. The silent black hole remains perfectly in place at the center of its galaxy, but it transitions into a much quieter, contemplative phase, consuming passing matter only on rare and occasional instances. This quiet, darkened fate may very well be what ultimately awaits to 618. In the unimaginably distant future, the roaring quasar will eventually grow dim as its surrounding reservoir of gas slowly dries up. The central black hole will remain infinitely enormous, yet it will sit in profound silence, largely inactive. Interestingly, a very similar transition has already taken place in our own cosmic backyard. The supermassive black hole nesting at the quiet heart of our Milky Way is currently resting in just such a tranquil, dormant state. Although it still occasionally devours small, stray pockets of gas, it no longer shines with the blinding, fierce radiance of a powerful quasar. Long ago, however, during its own tumultuous youth, it may have experienced a vastly more active and violent phase. Fascinating observations of giant, glowing gamma-ray structures towering above and below our galactic plane, known as the Fermi bubbles, suggest that Sagittarius A star may have unleashed powerful, energetic jets of plasma in the deeply distant past. By thoughtfully stacking those comparative steps, they slowly and beautifully build a mental picture that our fragile minds can begin to grasp, and step by step, we will begin to answer the profound question that brought us together here tonight. If this intriguing interpretation is correct, then our very own home galaxy once hosted a much brighter, far more tempestuous central engine than the relatively tranquil one we observe today. T618 represents a galaxy captured in the midst of one of its most breathtakingly dramatic and active phases. The supermassive black hole at its very heart has swollen to a truly mind-boggling size, while its surrounding accretion disk continues to radiate an extraordinary, almost unfathomable amount of energy into the cold void of space. By diligently studying such extreme systems, astronomers hope to slowly unravel the complex physical processes that allow these cosmic monsters to grow so unimaginably large. Every new observation carefully adds another vital piece to this grand cosmic puzzle. How massive were the original primordial seeds? How rapidly can the relentless process of accretion proceed under different, turbulent conditions? How frequently do giant galaxies collide and merge? And just how much raw gas flows eagerly toward their ravenous centers during those cataclysmic events? Just how incredibly big is TON 618? These profound questions remain highly active and exciting areas of modern research. New, sophisticated telescopes and advanced instruments continue to provide ever-clearer data, allowing dedicated scientists to study these brilliant quasars across vast, dizzying distances and meticulously explore the long history of black hole growth throughout the evolution of the universe. As those vital studies continue, magnificent objects like TON 618 remain among the most deeply fascinating examples of how gravity, time, and matter originally combined to sculpt some of the largest, most awe-inspiring structures in the entire cosmos. Gazing far away into the deep abyss of space is, in truth, a beautiful way of looking backward in time. Light does not travel instantaneously. Even though it sweeps through the cosmos faster than anything else in existence, it still requires precious time to cross the truly staggering distances that stretch between lonely galaxies. Because of this cosmic speed limit, when astronomers observe these incredibly distant objects, they are not seeing them as they exist in the present moment. Rather, they are witnessing them exactly as they were when that ancient light first began its epic journey. Really? This wonderfully simple idea carries a truly remarkable consequence. The farther away we look into the dark, the younger the universe appears to us. Nearby stars gently show us the present, familiar state of our own home galaxy, while more distant galaxies softly reveal what the cosmos looked like millions or even billions of years ago. Ultimately, the most distant quasars show us a wild universe that was still in its very early, tumultuous stages of development. The brilliant quasar powered by T618 belongs to this incredibly distant, ancient past. The ancient light reaching Earth today first began its lonely journey more than 10 billion years ago. At that distant epoch, the universe was only a mere fraction of its current age. Galactic structures were still actively forming and evolving, and the very first generations of stars had already lived their brief lives and died. In other words, the gargantuan black hole we observe in T618 had already grown to an extraordinary, almost impossible size very early in our cosmic history. This startling realization naturally raises a deeply fascinating question. How could such incredibly massive black holes appear so soon after the universe itself began? To even begin to answer that profound mystery, we must imagine what the pristine universe looked like during its earliest, most formative stages. Somewhere high above you right now, the velvet night sky is quietly and endlessly stretching in every single direction. Immediately after the hot Big Bang, the infant universe began expanding rapidly and cooling. In those earliest moments, it was filled with an extremely hot, dense mixture of energetic particles and intense radiation. Over time, as the temperature gradually dropped, floating protons and electrons finally combined to form the very first simple hydrogen atoms. For hundreds of millions of quiet years, the dark universe contained mostly cold hydrogen and helium gas. There were no bright stars yet, no swirling galaxies, just enormous, ghostly clouds of gas slowly drifting through the ever-expanding emptiness of space. Eventually, the invisible hand of gravity began pulling some of that scattered gas together. Small, subtle fluctuations in density grew progressively stronger over time, slowly allowing matter to gather into the very first gravitational structures. Within these dense, darkening regions, the cool gas collapsed further under its own weight, eventually igniting to form the first primordial stars. Astronomers often refer to these legendary early stars as population 3 stars. Unlike the stars we observe today, these pristine first stars formed entirely from pure hydrogen and helium. You might not be looking up at it at this exact moment. The heavier chemical elements we find in modern stars, such as carbon, oxygen, and iron, did not yet exist. Those complex elements would only be created much later through intense nuclear reactions deep inside stellar cores and during the violent, spectacular explosions of supernovas. Because this early primordial gas completely lacked those heavier elements, it behaved fundamentally differently during the delicate process of star formation. Modern gas clouds cool highly efficiently thanks to the presence of heavy metals and cosmic dust. This efficient cooling allows the gas to fragment into smaller, delicate pieces, eventually producing a multitude of stars of more moderate, gentle sizes. In the pristine infancy of the early universe, however, the stark absence of heavy elements meant that these primordial gas clouds cooled far less effectively. Consequently, as the gravity-bound gas collapsed inward, it inevitably formed much more colossal, gargantuan stars. Some of these ancient, luminous giants may have been hundreds of times more massive than our own familiar sun. Yet, such massive stars are destined to live tragically short lives. Perhaps the warm curtains are closed, or the soft lights are turned off, and you are already resting peacefully. They burn through their precious nuclear fuel with ferocious speed, ultimately ending their brilliant existences in cataclysmic, violent explosions known as supernovae. In certain dramatic instances, the sudden collapse of the dying stellar core leaves behind a dense black hole. These primordial dark remnants may have served as the vital first seeds for the gargantuan, supermassive black holes we observe in the cosmos today. A singular seed black hole, born from the heart of a massive early star, might begin its journey with a collective mass of tens or perhaps even hundreds of suns. From that modest starting point, it could gradually begin growing by relentlessly pulling in the surrounding, drifting gas. Yet, it is precisely here that the cosmic puzzle becomes infinitely more complicated. Even if a black hole continuously and voraciously consumes matter, its ultimate growth rate is strictly limited by the Eddington limit, the delicate, precarious balance between the relentless inward pull of gravity and the powerful outward push of radiation generated by the swirling accretion disk. This fundamental cosmic limit inevitably slows the feeding process to a measured crawl. When modern astronomers meticulously calculate how long it would take such a small, humble seed black hole to expand into an entity as unimaginably massive as T618, the required time appears almost uncomfortably, impossibly long. Maybe the sky outside is thick with clouds, hiding the stars. Indeed, in several perplexing cases, this calculated growth period seems longer than the actual age of the universe itself at the precise epoch when we observe the shining quasar. This paradox strongly suggests that something far more extraordinary must have transpired during the dawn of the early universe. One intriguing possibility is that certain black holes began their existence with much larger initial masses. Instead of slowly forming from the debris of individual dying stars, these massive black holes might have emerged through a process of direct collapse. In this fascinating scenario, a colossal, undivided cloud of gas collapses directly into a singular black hole, without ever fragmenting into a cluster of stars. If the primordial gas cloud is sufficiently massive, the resulting black hole could begin its life with an astonishing mass of tens of thousands, or perhaps even hundreds of thousands of solar masses. Starting with such a tremendously larger seed would make it infinitely easier to grow into an ultramassive black hole within a mere few billion years. Another crucial factor that may have dramatically helped these early black holes grow so quickly is the sheer, overwhelming abundance of pristine gas within young, developing galaxies. The early universe contained vast, untapped reservoirs of raw hydrogen gas that had not yet been converted into burning stars. This abundant gas could flow steadily and heavily toward the gravitational centers of galaxies, richly feeding the swirling accretion disks around hungry, young black holes. Or maybe it is glowing softly and warmly with the ambient light of a bustling city that never completely sleeps. Violent collisions between fledgling galaxies were also far more common during this turbulent, ancient era. When these galaxies merge, their vast gas clouds become profoundly disturbed and intensely compressed. These chaotic gravitational disturbances can drive immense amounts of gas directly toward the center of the newly combined galaxy. If a black hole already resides there, it can begin consuming this fresh influx of gas at a rapid, terrifying pace. The spectacular result of this feeding frenzy may be an intense, brilliant period of active quasar luminosity. During such a frantic phase, the growing black hole expands with breathtaking speed, while simultaneously releasing an enormous, blinding torrent of energy into its cosmic surroundings. This may be exactly the dramatic sequence of events that occurred in the case of the monstrous TON 618. This particular black hole may have experienced several successive episodes of rapid, explosive growth, fueled by spectacular, gas-rich mergers in the early universe. Each successive episode would add immense mass to the black hole while dramatically increasing the brilliant brightness of the surrounding quasar. Over vast epochs of time, these monumental feeding events could eventually produce the truly astronomical mass we observe today. But whether we can see it or not, that infinite sky is always there. Dedicated astronomers continue to search tirelessly for tangible evidence of these early, rapid growth processes by carefully studying luminous quasars across vast, varying cosmic distances. Because light takes a finite amount of time to travel across the vast emptiness of space, observing these very distant, ancient quasars allows modern scientists to examine black holes during different, critical stages of cosmic history. Some of these brilliant quasars appear to us from an epoch when the young universe was only a single billion years old. Yet, these incredibly early quasars already harbor central black holes with staggering masses equivalent to billions of suns. Their astonishing existence strongly suggests that cosmic black hole growth can proceed with remarkable, unprecedented speed under the right cosmic conditions. Even now, modern telescopes continue to push these profound observations. Further, the revolutionary James Webb Space Telescope has finally begun observing ancient galaxies and luminous quasars from the extremely early primordial periods of cosmic history. Its extraordinarily powerful infrared instruments allow astronomers to delicately detect the faint, whispered light from celestial objects that formed not long after the very first stars flickered into existence. Each wondrous new observation precious helps scientists continuously refine their deep understanding of how these monstrous black holes and their host galaxies beautifully evolved together. A vast, majestic ceiling of space that perpetually surrounds our small, blue planet on all sides. The breathtaking picture that gradually emerges is one of a remarkably dynamic and chaotic early universe. Vast streams of cold gas flowed restlessly through young, developing galaxies. Brilliant stars rapidly formed and spectacularly exploded. Meanwhile, supermassive black holes grew with astonishing rapidity at the very centers of these turbulent systems. Over billions of years, these violent yet creative processes slowly fashioned the enormous cosmic structures we marvel at today. The legendary Tun 618 represents one of the most dramatic, awe-inspiring outcomes of that early cosmic evolution. Its central black hole grew to a colossal size rarely ever seen even in our vast modern universe. Yet, despite its absolutely enormous mass, this cosmic titan still faithfully follows the very same fundamental, elegant rules of gravity that quietly govern every other humble black hole in existence. Numbers that describe the infinite universe often grow so incomprehensibly large that they begin to feel almost abstract, slipping away from our human comprehension. When astronomers speak of billions of glittering stars, trillions of silent kilometers, or black holes weighing tens of billions of suns, the fragile human mind struggles profoundly to attach a clear, tangible picture to those staggering values. If you have ever stepped outside on a perfectly clear night, far away from the blinding city lights, you probably remember that breathtaking feeling of awe. It becomes far too easy to treat these cold numbers as mere mathematical symbols rather than something that represents majestic, real structures existing somewhere in the deep, silent expanse of space. Yet, extraordinary objects like Tun 618 strongly challenge us to confront those overwhelming numbers much more carefully. Because once astronomers began meticulously measuring the unique properties of this distant quasar and the truly enormous black hole actively powering it, a much deeper, more philosophical question slowly emerged. It was not just a question of how spectacularly large this particular black hole is, but whether there exists an absolute, fundamental limit to how large black holes can possibly become in our universe. At first glance, it might seem as though these insatiable black holes could grow forever without any upper boundary. Relentless gravity pulls all nearby matter inward, and if enough swirling gas and cosmic dust remain readily available, the black hole simply continues gaining mass indefinitely. Host galaxies violently collide, vast reservoirs of gas flow directly toward the darkened center, doomed stars fall helplessly inward, and colossal black holes merge majestically with one another. Over billions of patient years, all of these grand cosmic processes could, in principle, allow a black hole to grow completely without limit. Yet, when astronomers examine the deep universe with meticulous care, they notice something deeply interesting. Most supermassive black holes appear to fall within a surprisingly specific range of masses. The very first thing many people notice is just how many countless stars there are. Many contain several millions of solar masses. Some reach impressively into the billions. An even smaller, rarer number climb into the tens of billions, but beyond that extreme threshold, such objects become increasingly scarce. Tun 618 sits precariously near the very upper edge of what astronomers currently observe in the cosmos. Its staggering mass, estimated at around 66 billion times that of our Sun, firmly places it among the largest known black holes in existence. Such an incomprehensible scale already severely stretches the limits of human imagination. But it also raises an incredibly important, profound scientific question. Is this colossal size close to the absolute maximum that nature itself allows? To explore that fascinating possibility, astronomers carefully consider the physical processes that allow black holes to grow. As we discussed earlier, the most critically important mechanism is accretion. Not just a small handful sparsely scattered across the dark sky, but thousands upon thousands of faint, delicate points of ancient light quietly and beautifully shining. Wisps of gas from the surrounding galaxy form a massive, rapidly rotating disk and gradually spiral inward, slowly feeding the insatiable black hole. Each individual parcel of gas adds more precious mass to the dark central object. But this accretion process does not continue unchecked forever. When matter falls precipitously toward a black hole, the friction within the accretion disk causes it to become extremely, intensely hot. That fierce heat produces an enormous, shining radiation which fiercely pushes outward against the incoming gas. Eventually, a delicate balance forms between the relentless inward pull of gravity and the powerful outward pressure of this radiation. This beautiful astrophysical balance is known as the Eddington limit. When a black hole reaches the Eddington limit, the intense radiation emanating from the swirling accretion disk becomes strong enough to violently blow away some of the surrounding gas. The black hole can still grow, but its growth rate becomes strictly regulated by this eternal cosmic balance between gravity and radiation. This natural limit ultimately slows down the chaotic feeding process. From unimaginable, gargantuan distances away. Even if enormous, seemingly limitless amounts of gas are readily available, the ravenous black hole cannot consume all of it instantly. Instead, it grows gradually, expanding with a patient grace as matter continues spiraling slowly inward. Over vast, epochal periods of time, that gradual growth can still produce extremely massive black holes. But the Eddington limit acts like a natural speed limit, quietly preventing runaway growth from happening too quickly. Another crucial factor that influences the maximum size of black holes involves the very galaxies that host them. Most supermassive black holes live at the deep centers of galaxies, and their growth depends heavily on the supply of gas available in those surrounding environments. If the galaxy contains large, rich amounts of gas, the black hole can continue feeding. But if the galaxy's gas becomes depleted, either because it actively forms new stars, or because it is violently blown away by intense radiation and powerful jets, the black hole's growth slows dramatically. Over time, the host galaxy and its central black hole reach a delicate kind of equilibrium. The black hole profoundly influences the galaxy through torrents of radiation and energetic outflows, while the galaxy, in turn, controls the supply of matter available for accretion. At first glance, they all seem to look almost exactly the same. This intimate relationship beautifully explains why astronomers observe a strong, undeniable correlation between the mass of a galaxy's central black hole and the overall mass of the galaxy's central bulge. The two seem to grow together, harmoniously shaping each other's evolution over billions of years. In this context, the enormous, staggering size of Ton 618 suggests that its host galaxy must also be extremely large. Although the galaxy itself is quite difficult to observe because of the intense, blinding brightness of the quasar, it likely contains vast, rich amounts of matter. That matter would have provided the abundant fuel needed to build such an enormous, majestic black hole. Another grand growth mechanism also plays a vital role in determining the ultimate size of black holes: galaxy mergers. When two massive galaxies collide, their central black holes may eventually spiral together and merge. This cataclysmic process adds their masses together, producing a single, even larger black hole. Over vast cosmic time, repeated merges can gradually increase the size of central black holes in massive galaxies. T618 may represent the ultimate outcome of many such historic events. Delicate, tiny dots of light, some glittering with intense brightness while others whisper dimly, yet they remain mere flickering points against the vast, consuming darkness. If its host galaxy merged with several other large galaxies during its long history, each individual merger would have delivered additional gas and possibly another black hole directly to the center. These spectacular events would greatly accelerate the growth of the central object. But even merges have limits. Galaxies do not collide endlessly. The number of large galaxies available for merges decreases over time as the universe expands and galaxy clusters settle into stable, peaceful structures. Eventually, the rare opportunities for massive black holes to merge become far less frequent. When astronomers combine these diverse factors, the Eddington limit, the finite supply of gas within galaxies, and the rate of galaxy merges, they begin to see why ultra-massive black holes like T 618 are exceptionally rare. Nature graciously provides several pathways for black holes to grow, but each pathway includes natural mechanisms that slow the process down. These limits do not impose a strict, absolute maximum size. Instead, they make extremely large black holes increasingly unlikely. And yet, remarkably, each and every one of those fragile pinpricks of light represents something truly colossal. Even so, daring theoretical models suggest that black holes larger than Ton 618 could indeed exist. Some simulations indicate that black holes might reach staggering masses of 100 billion solar masses under highly favorable conditions. Such colossal objects would require exceptionally massive galaxies and long, uninterrupted periods of sustained accretion. They would likely reside in the most massive galaxy clusters in the universe. Observationally, astronomers have identified a few rare candidates that may approach this extreme range. Although the measurements remain highly uncertain, 618 remains one of the clearest and most definitive examples of an ultramassive black hole with a well-studied quasar. Its awe-inspiring existence shows that the universe is capable of building black holes far larger and infinitely more terrifying than the silent giant resting at the very center of our own home galaxy, Sagittarius AR. This cosmic anchor, Sagittarius A star, contains about 4 million solar masses, a number that sounds monumental until we look outward. Compared with the staggering tens of billions of solar masses contained within the colossal structures like tons, that profound difference is almost impossible for the human mind to fully grasp. The vast majority of them are grand, luminous stars far larger and more majestic than our own sun. The dramatic contrast beautifully highlights how breathtakingly diverse black holes can be across the vast tapestry of the universe. Some exist as relatively small, quiet remnants of once brilliant collapsed stars, drifting silently through space. Others slowly grow into supermassive anchors, holding entire galaxies together at their very centers. And then, a rare and majestic few reach a truly ultramassive scale, where their silent event horizons alone span vast regions of space far larger than entire planetary systems. Studying these extraordinary objects, such as the monstrous 618, allows astronomers to courageously explore the absolute, extreme limits of this cosmic range. By meticulously measuring their unfathomable masses, carefully analyzing the faint light of their spectra, and intricately modeling the violent environments that surround them, scientists can rigorously test our fragile theories about how black holes grow and how their host galaxies gracefully evolve over deep time. These profound studies do not merely satisfy our curiosity. They also help reveal the grand, majestic structure of the observable universe. The distribution of distant quals across cosmic time tells us precisely when these primordial black holes were most actively feeding upon the surrounding cosmos. The monumental masses of those ancient black holes provide invaluable clues about the dense, chaotic conditions that governed early galaxies. Some belong to impossibly distant, swirling galaxies that contain hundreds of billions of stars. In a very real way, the Titan 618 acts as a brilliant cosmic laboratory, allowing earthbound astronomers to study the absolute majesty of gravity operating at one of its most terrifyingly powerful scales. And as dedicated researchers continue to discover new, luminous quasars and measure the immense masses of their central black holes, they move ever closer to answering a fundamental question that has deeply fascinated scientists for decades. Is there truly a definitive, physical maximum size that a black hole can ever reach? Or could the cold, dark universe still be hiding even more colossal giants, lurking silently somewhere in the deepest, unexplored depths of space? If the fertile cosmos was indeed capable of producing something so incredibly large, is it not reasonable to wonder if it could also produce something even more monstrously immense? At a fleeting, first glance, the answer to this mystery might seem deceptively simple. The universe is, after all, unimaginably enormous. It contains hundreds of billions of sprawling galaxies, and almost every single one of those galaxies may host its own dark, central black hole. Given such staggering, mind-boggling numbers, it feels entirely reasonable to assume that somewhere out there, cloaked in darkness among those countless galaxies, an even larger black hole must surely exist. But when astronomers begin examining the physics of the problem with careful precision, the question becomes infinitely more intriguing. Others are cosmic objects so fiercely energetic that they completely outshine entire galaxies all by themselves. Because while there is no simple, absolute law of physics that explicitly declares a black hole cannot grow any larger than the magnificent N618, several subtle, yet powerful, physical factors begin to make the formation of such enormous objects increasingly difficult to form. Truly understanding those cosmic barriers requires us to think deeply once again about how these monstrous black holes actually grow in the first place. As we have discussed earlier, The most common evolutionary path toward becoming a supermassive black hole involves two primary majestic processes. The first of these is accretion, a violent yet beautiful dance where vast clouds of gas and dust spiral helplessly inward through a glowing accretion disk, gradually feeding and adding mass to the central black hole. The second process is merging, an epical event where two monstrous black holes collide and seamlessly combine into a single, far larger entity after their parent galaxies slowly merge. While both processes actively contribute to the relentless growth of these extremely large black holes, both are also bound by strict, natural limits. Let us consider the mechanism of accretion first. When cold, drifting matter falls helplessly toward the event horizon of a black hole, it releases absolutely enormous amounts of energy as it frictionally heats up within the swirling accretion disk. This bound energy escapes into the dark void in the form of blinding radiation, visible light, intense ultraviolet energy, and piercing X-rays. The most baffling, beautiful secret of the night sky is just how masterfully it conceals its true, staggering scale. But that ferocious radiation does not simply stream harmlessly and quietly into the empty space. It also exerts a powerful outward pressure on the surrounding reservoirs of gas. If the central black hole begins feeding too quickly and voraciously, this outward radiation pressure becomes strong enough to violently push the nearby gas away, blowing it into deep space before it ever has a chance to fall inward. This delicate, eternal cosmic balance between gravity pulling the cold gas inward and the intense radiation pressure pushing it outward defines what scientists call the Eddington limit. While the Eddington limit does not completely halt the black hole's relentless growth, it dramatically slows the entire process down. Even if a host galaxy contains a vast, virtually endless supply of pristine gas, the hungry black hole simply cannot consume all of it at once. Instead, it must grow slowly and gradually, as the feeding material spirals inward at a measured rate that does not violate this delicate cosmic balance. Over the millions or billions of years that gradual, patient feeding can still produce truly gargantuan black holes. Yet, as the eons slowly drift by, it becomes increasingly difficult to sustain the delicate, turbulent conditions required for such ceaseless, uninterrupted growth. Looking up, everything appears so deceptively small. Inevitably, the host galaxy itself begins to undergo a profound transformation. As vast reservoirs of cosmic gas are either greedily consumed by the central monster or gently kindled into newborn stars, the overall supply of available matter steadily decreases. At the same time, the fiercely blinding radiation and powerful jets erupted by an active, blazing quasar can forcefully drive gas far away from the galactic core. In a poetic irony, the black hole's very own violent activity ultimately serves to limit its own future growth. This exquisite, self-regulating cosmic process helps explain why the vast majority of supermassive black holes eventually fall within a remarkably specific range of masses. Even within the grandest of galaxies, the precious cosmic fuel inevitably becomes scarce. The cataclysmic merging of black holes can also dramatically contribute to their growth. But here too, the grand opportunities of the cosmos are strictly limited. Galaxies do indeed collide and merge, most frequently in the ancient, crowded dawn of the early universe when they drifted much closer together. When these colossal stellar islands collide, their central black holes will slowly spiral toward one another in a gravity-locked waltz, ultimately coalescing into a single, even more formidable entity. Every such cosmic union substantially increases the final mass of the newly formed Titan. Everything feels serenely calm, peaceful, and infinitely distant. Yet, on the immense, sweeping scales of cosmic time, these dramatic galactic mergers remain relatively rare occurrences. As the universe expanded and galaxies drifted further apart, settling into quiet clusters and groups, the frequency of these violent collisions naturally began to decline. Consequently, while mergers can indeed construct larger black holes, this process cannot endure indefinitely, as the number of neighboring cosmic partners eventually runs out. Even so, the patient universe has had billions of years to slowly assemble these truly colossal structures. When modern astronomers gaze deep into the hearts of giant, ancient galaxies, they occasionally discover silent monsters that remarkably approach the mind-boggling scale of T618. Some astonishing scientific estimates suggest that the most gargantuan of these black holes may possess a staggering mass equivalent to nearly 100 billion of our suns. These terrifyingly majestic entities are fittingly whispered of as ultramassive black holes. They reside almost exclusively within the largest host galaxies situated at the very hearts of massive galaxy clusters, dense, chaotic regions where countless galaxies have merged over vast epochs of time. In these exceptionally crowded environments, the nurturing conditions for growth can remain highly favorable for far longer than in quieter, more isolated galaxies. Abundant reservoirs of pristine gas continue to nourish the central black hole, while successive, titanic mergers perpetually contribute additional mass. Even the most colossal structures in the entire universe shrink down to minuscule, fragile specks when we view them from our tiny vantage point here on Earth. Yet, even within these extreme cosmic nurseries, black holes exceeding the threshold of 100 billion solar masses remain exceedingly rare anomalies. A significant part of the reason lies within the deep, intimate relationship between these central abysses and their host galaxies. Astronomers have observed that the staggering mass of a galaxy's central black hole closely scales with the grand mass of the galaxy's central stellar bulge. This harmonious correlation strongly suggests that black holes and their galaxies grow in tandem, sharing a common destiny. As the black hole swells in mass, the titanic, raw energy it unleashes can profoundly influence the surrounding galaxy, heating ambient gas and driving powerful, sweeping outflows into the void. Eventually, this relentless feedback chokes off the supply of pristine gas required for further cosmic growth. In a profound sense, the sovereign black hole actively regulates the evolutionary destiny of its own host galaxy. If the dark behemoth grows too powerful, its furious energy will completely block the host galaxy from delivering any further fuel to its insatiable center. The legendary Ton 618 stands as perhaps one of the most extreme, awe-inspiring examples of this delicate cosmic equilibrium. This monstrous black hole grew exponentially during an ancient, fertile epoch when massive, unchecked reservoirs of gas were readily available. This creates a beautiful yet profound illusion. Today, we observe it across the vast gulfs of time as a brilliantly luminous quasar, shining spectacularly across billions of light-years of space. Yet, this extraordinarily radiant phase is not destined to last forever. Over the slow march of time, the surrounding fuel supply will inevitably diminish. The magnificent quasar will slowly fade into darkness, leaving behind a silent, invisible titan that forever shapes the silent motion of stars within its host galaxy. Astronomers sometimes dare to imagine what a truly gigantic black hole might look like if it dared to surpass the unimaginable scale of 2618. The dark boundary of its event horizon alone would stretch across vast, cold distances far larger than entire planetary systems. The swirling, white-hot accretion disk surrounding this abyssal mouth might span immense regions easily comparable to the size of a solar system, or perhaps even vastly larger. Colossal jets of pure energy could stretch for tens of thousands of silent light-years, piercing deep into the cold, empty voids of intergalactic space. And yet, despite this staggeringly immense scale, the fundamental laws of physics would remain beautifully unchanged. When we casually glance upward, the universe does not seem overwhelmingly large. Gravity would still inexorably warp and curve the very fabric of spacetime around the abyss. Swirling matter would continue to spiral helplessly inward through a glowing accretion disk. Blazing radiation and powerful jets would carry radiant energy far outward. The elegant laws of general relativity would continue to govern the mysterious structure of the event horizon. Even the most monstrous black holes obey the exact same quiet rules as the smallest stellar remnants. The only true difference lies in their unimaginable scale. The breathtaking existence of cosmic titans like Ton 618 serves as a constant, humbling reminder to astronomers that our universe is capable of sculpting structures far grander than early scientists ever dared to imagine. For quiet centuries, our own sun was regarded as the ultimate, typical standard of cosmic grandeur. Yet, as time marched on, astronomers gazed deeper to discover stars that dwarfed our sun into insignificance. Then, they mapped majestic galaxies harboring hundreds of billions of brilliant stars. Instead, it appears peaceful, quiet, and almost comfortingly manageable. Today, they observe supermassive black holes containing tens of billions of solar masses. Each profound discovery gently pushes the boundaries of our understanding of cosmic scale just a little farther into the unknown. And yet, even after uncovering such colossal giants as Tun 618, the universe likely still harbors deep, unfathomable secrets. The observable universe contains an almost infinite, staggering number of galaxies. Many of these celestial islands lie far beyond the faint, reaching grasp of our most advanced modern telescopes. In those incredibly distant, untouched regions of the cosmos, there may well exist gargantuan black holes that have quietly grown under primordial conditions we have not yet even begun to comprehend or fully explore. Future astronomical observations will undoubtedly reveal objects even more breathtakingly massive than the titans we know today. Revolutionary new telescopes, highly sensitive instruments, and deeper, more meticulous surveys of the starry skies will continuously expand our fragile view of the cosmos. Every single discovery will gently help astronomers refine their understanding of how these dark giants grow and how parent galaxies slowly evolve. And though TON 618 currently remains one of the largest, most formidable black holes known to humanity, it surely does not represent the absolute, final limit of creation. Yet, that gentle impression dissolves rapidly the moment we dare to ask one deceptively simple question. How incredibly vast are the things we are actually gazing upon? Somewhere out there, softly hidden among the most distant and ancient galaxies, the creative universe may still be building something far, far larger. Picture, if you will, a lonely spacecraft drifting silently through the cold, eternal darkness that lies between galaxies. The powerful engines are completely silent now, the long, arduous phase of acceleration having finished many years ago, and the vessel is simply, effortlessly coasting through the endless void. Outside the panoramic observation windows, the stars appear perfectly steady and infinitely distant, scattered like brilliant diamonds across a deep, velvet black sky that stretches boundlessly in every direction. Somewhere far ahead, shrouded in the distant mist of time, lies the host galaxy harboring the brilliant, terrifying quasar powered by 618. At the very beginning of this monumental journey, there was nothing unusual for the human eye to behold. Even our most powerful telescopes could show to N618 as little more than a tiny, shimmering point of light. Viewed from billions of light-years away, the entire host galaxy collapses into a minute, fragile speck against the overwhelming darkness of the void. The central black hole itself remains utterly invisible to the naked eye. Only the fiercely brilliant radiation pouring from the active quasar reveals that something truly extraordinary dwells there. To seek an answer to that grand question, astronomers have had to construct an entirely new, mind-bending way of thinking about size and spatial distance. Yet, as the spacecraft slowly and steadily approaches, that faint, whispering point of light begins to grow perceptibly brighter. Over the passing years, what once resembled a single, lonely star-like dot gradually resolves into the majestic shape of a distant galaxy. Billions of shining stars slowly fill the velvet sky ahead, forming a magnificent, luminous structure that gracefully rotates through the quiet of space. Swirling spiral arms or glowing, elliptical clouds of pristine starlight stretch vast distances across tens of thousands of light-years. The host galaxy itself begins to appear grand and enormous long before the central black hole ever becomes visible. Even from this immense distance, the core region of the galaxy shines with an unusual, brilliant intensity. That blazing brightness is born from the active quasar, where unfathomable torrents of superheated gas are spiraling frantically inward toward the central gravitational abyss. Blinding radiation pours relentlessly outward from that chaotic region, carrying immense, unimaginable energy across the cold intergalactic space. As the quiet spacecraft draws closer to the galaxy, this central glow grows steadily more intense and mesmerizing. The individual stars surrounding the dense galactic core become far easier to distinguish. The sheer scales involved in the cosmic theater are so incomprehensibly massive that our ordinary, everyday units like kilometers or miles quickly cease to be of any real help. Their stellar orbits begin to curve visibly around a silent, invisible center where gravity absolute dominates the motion of everything nearby. At the very heart of this cosmic dance lies the colossal black hole itself. Still invisible, still deeply hidden behind its mysterious event horizon. The quasar surrounding it, however, becomes increasingly and spectacularly dramatic. Vast gas clouds swirl tumultuously through the central region, forming an enormous, glowing accretion disk that shines with an extraordinary, brilliant brightness. This gargantuan disk is not flat and static like a solid plate, but behaves much more like a fiercely glowing, turbulent whirlpool of superheated plasma, circling endlessly around the yawning mouth of the black hole. Temperatures in these innermost regions easily reach unimaginable heights of millions of degrees. Intense radiation emerges across a vast spectrum of wavelengths, manifesting as brilliant visible light, searing ultraviolet energy, and incredibly powerful X-rays. To approach this hostile region would surely require extraordinary, highly advanced shielding. Let us begin our journey with something comforting and familiar. The chaotic radiation environment lingering near a quasar can be extremely, violently intense. Any courageous spacecraft venturing too close would desperately need robust protection against the onslaught of highly energetic particles streaming relentlessly outward from the churning accretion disk and the surrounding superheated gas. Yet, even when observed from a comfortably safe distance, the panoramic view would remain utterly remarkable. The disk would appear as a breathtakingly brilliant ring of celestial light, starkly encircling a profound, dark central region. That absolute darkness marks the silent location of the event horizon, the ultimate boundary where gravity becomes so overwhelmingly strong that even light itself cannot hope to escape. For a supermassive black hole as colossal as Neptune 618, this event horizon spans a truly astonishing, mind-boggling distance. As we previously discussed, its immense diameter stretches across hundreds of billions of kilometers. To put this unimaginable scale into perspective, imagine placing this monstrous black hole directly at the center of our own solar system. Its dark event horizon would extend far beyond the lonely, icy orbit of Neptune. A traveling spacecraft approaching the black hole would therefore encounter its immense gravitational influence long before ever reaching the actual event horizon itself, even at distances of thousands of millions of kilometers away. The distance separating the Earth from our moon is roughly 384,000 kilometers. The colossal gravity of the black hole would already be actively shaping the elegant motion of nearby gas clouds and orbiting stars. Yet, curiously, gravity behaves in remarkably different ways near such an enormous, unprecedented object. For much smaller black holes, the localized tidal forces near the event horizon become extremely, violently strong. The stark difference in gravitational pull between the front and the back of an approaching object can stretch it dramatically, tearing it apart as it draws closer to the fatal boundary. This bizarre and terrifying effect is often evocatively described as spaghettification. But Neptune 618 is so unfathomably massive that its event horizon lies incredibly far from the hidden central singularity. Because of this gargantuan scale, the gravitational tidal forces acting at the event horizon would actually be relatively, surprisingly gentle compared with those found around smaller black holes. A spacecraft crossing the fateful threshold of such a cosmic giant might not experience any dramatic, destructive stretching immediately. Instead, the transition could feel surprisingly, deceptively calm at first. Of course, from the external perspective of a distant observer watching the spacecraft slowly approach the event horizon, something very strange and surreal would appear to unfold. By our everyday terrestrial standards, that already feels immensely far. As the vessel draws closer to the inescapable boundary, the very light it emits becomes increasingly, profoundly affected by the tightening grip of gravity. According to the groundbreaking theory of general relativity developed by Albert Einstein, immensely strong gravitational fields dramatically slow the passage of time relative to distant, motionless observers. This means that physical clocks near the black hole tick noticeably more slowly than clocks resting far away in quieter realms of space. To an onlooker watching from a safe, comfortable distance, the descending spacecraft would appear to gradually slow down to a crawl as it approaches the event horizon. Its outgoing signals would become stretched into much longer, weaker wavelengths. The emitted light would slowly, beautifully redden and fade away. Eventually, the spacecraft would appear almost frozen in time at the absolute edge of the black hole, its spectral image growing dimmer and dimmer until it finally disappeared entirely into the dark void. Yet, for the brave travelers journeying aboard the spacecraft, the subjective experience would feel very different indeed. Inside the quiet confines of the ship, time would continue to pass perfectly normally. The crew would look out to see the brilliantly glowing accretion disk completely surrounding them, its intense light bending gracefully around the black hole due to the profound effects of gravitational lensing. Driving such a distance would require several long, exhausting days without a single stop. Distant stars positioned behind the black hole would appear warped into surreal, glowing arcs and perfect rings as their ancient light curves around the intense, dominant gravitational field. This majestic bending of light creates one of the most dramatic and hauntingly beautiful visual effects near a black hole. The central abyss of the black hole itself would manifest as a profoundly dark, silent sphere, set in stark, breathtaking contrast against the luminous background of the swirling accretion disk and the glittering tapestry of distant, ancient stars. The surrounding radiance would bend and curve elegantly around its impenetrable edge, fashioning a ghostly, distorted halo of light. As the intrepid spacecraft finally crossed the threshold of the event horizon, there would be no physical barrier to behold, no sudden, jarring impact, only a quiet, almost poetic passage into a desolate region of space where any hope of escape becomes utterly impossible. From that fateful moment onward, every conceivable path through the warped fabric of spacetime would inevitably lead inward, spiraling relentlessly toward the absolute center. The crew within might still gaze out and observe the fading universe for a fleeting moment, but any desperate signals they attempt to transmit outward would be forever trapped, unable to break free from the black hole's inescapable, overwhelming gravity. Flying that same stretch in a modern airplane would take many endless hours. Eventually, their silent journey would draw them deeper still into the crushing heart of the abyss, where gravity becomes incomprehensibly overwhelming. Exactly what lies at the absolute center of a black hole remains one of the most profound and tantalizing mysteries in the realm of modern physics. Einstein's general theory of relativity predicts a singularity, a microscopic point where density reaches a terrifying infinity, and the familiar, reassuring laws of physics utterly break down. Many visionary physicists believe that a grander, deeper theory, one that harmoniously unites gravity with the chaotic world of quantum mechanics, will eventually illuminate this darkness and reveal a far more complete picture of reality. For now, however, the mysterious interior of a black hole remains eternally hidden behind the dark veil of the event horizon. Absolutely no information, not even a single whisper of light from that isolated region, can ever hope to reach the outside universe. Even so, merely imagining a grand journey toward a supermassive black hole like T618 helps us deeply appreciate the truly staggering scales involved in our vast cosmos. The colossal event horizon alone stretches across immense distances that easily dwarf entire planetary systems. The brilliant accretion disk surrounding this monster shines with a fierce radiance, far brighter than billions of stars in entire galaxies combined. And the formidable gravitational field near the black hole warps the very fabric of space and time in profound ways that deeply challenge our comfortable, everyday understanding of physical reality. Yet, in the grand, sweeping vocabulary of astronomy, our moon is practically resting right next door. All of this cosmic drama unfolded in an incredibly distant galaxy, whose ancient light has traveled across the dark void for billions of years just to finally reach our eyes. From our modest Earth, T618 appears only as a tiny, unassuming point of light lost in the night sky. Yet, safely hidden behind that faint, delicate glow lies one of the most monstrously powerful gravitational engines ever discovered in the cosmos. And contemplating such unimaginably enormous objects inevitably gently guides us back to a simpler, quieter question. After exploring these immense cosmic scales and distant, wondrous structures, what does all of this ultimately tell us about the fragile, beautiful universe we inhabit? Step outside on a quiet, calm evening and look up at the heavens for just a brief moment. At first glance, the night sky rarely looks particularly dramatic or chaotic. Only a few exceptionally bright stars may stand out against the darkness. Perhaps, if you find yourself far enough from the intrusive glare of city lights, a faint, delicate band of milky light stretches gracefully across the celestial dome. Wandering planets might appear as serene, steady points of light, refusing to twinkle as restlessly as the surrounding stars. A beam of light traveling from the moon reaches Earth in just a fraction over a single second. For most of us, this quiet view feels deeply peaceful, comforting, and familiar. Absolutely nothing about that quiet, silent scene suggests the gargantuan structures and violent energies that exist far beyond what the human eye can easily perceive. And yet, mysteriously hidden within that calm, dark sky are cosmic objects whose unbelievable sizes and unimaginable energies stretch far, far beyond the limits of ordinary human experience. Among these celestial wonders is the incredibly distant quasar, powered by the colossal T618. When astronomers peer through their most powerful telescopes to observe that enigmatic object, they see only a minuscule, tiny point of light. From Earth, it does not appear particularly large or unusual at all. Indeed, without careful, meticulous analysis, it could easily be mistaken for just another ordinary, distant star. But that faint, deceptively quiet point of light actually represents one of the most colossal black holes currently known to science. Its dark event horizon alone stretches majestically across a vast region of space far larger than our entire solar system. Superheated gas spiraling relentlessly around it forms a brilliantly glowing accretion disk, releasing an absolutely enormous amount of energy into the void. Fierce jets of powerful radiation may shoot outward across unimaginable distances that easily rival the very size of entire galaxies. Now, let us compare that cozy distance to the vast gulf between the Earth and our life-giving Sun. All of this violent, spectacular activity is taking place billions of light-years away from our quiet home. And the ancient light we observe today began its long, lonely journey across the cosmos long before the very first human civilization ever existed. When that pristine light first left its distant source, our Earth was already billions of years old. Yet life on our blue planet was still slowly, patiently evolving toward the diverse forms we recognize today. Great continents were shifting slowly and silently across the planet's surface, and ancient, primitive ecosystems were continuously changing. The earliest, faint ancestors of modern animals were only just beginning to slowly spread across the land and sea. During that same era, the quasar around T618 was already shining with an unimaginable, brilliant intensity in its own far-off primordial galaxy. This ancient, radiant light embarked on a monumental journey across the endlessly expanding cosmos, silently traversing vast, lonely regions of space populated by swirling galaxies, newborn stars, and mysterious reservoirs of unseen dark matter. For countless billions of years, through the deep silence of the void, that tireless beam of light continued its solitary journey. Eventually, a minuscule, almost miraculous fraction of those ancient photons finally drifted into the quiet region of space that would much later coalesce to become our own solar system. Our blue planet orbits this blazing star at a staggering average distance of about 150 million kilometers. Yet even then, their grand pilgrimage was far from over. They still had vast distances to cross. When the Earth itself slowly congealed and formed roughly 4.5 billion years ago, these photons were still hurtling through the darkness. For the vast majority of our planet's long history, no conscious creatures existed upon its surface who could look up and observe the starry night sky with a systematic scientific curiosity. Thus, the ethereal light from 2618 continued its steady stream through the dark void, while primitive life slowly and painstakingly evolved on our warm, wet planet. Only in the most fleeting, recent moments of cosmic history did a curious species called humans begin crafting sophisticated instruments capable of detecting such incredibly distant quasars. Armed with powerful telescopes and delicate spectrographs, early astronomers patiently learned how to capture and study the faint, ghostly light whispering to us from these remote, ancient galaxies. By meticulously analyzing the delicate, rainbow-like spectrum of that ancient starlight, They uncovered the unmistakable signatures of violently fast-moving gas swirling near colossal, lurking black holes. That is precisely how TS-618 was eventually recognized and understood for what it truly is. It was not a simple star, nor even a conventional galaxy, but a magnificent quasar powered by one of the most gargantuan, unimaginably massive black holes ever detected or measured by human intelligence. The astonishing discovery of celestial objects like this has gradually but profoundly reshaped the very foundations of how we perceive and understand our vast universe. This astronomical figure is so incredibly vast that scientists routinely simplify it into a unique, elegant unit known as the astronomical unit, or simply AU. For almost all of recorded human history, the velvet night sky had appeared comforting and relatively simple. The shining stars seemed eternally fixed in their places, weaving familiar patterns that repeated predictably, night after beautiful night. Our ancient ancestors gazed upward and used those comforting patterns for practical navigation, poetic storytelling, and the drafting of early calendars. Yet, the true, infinitely deeper structure of the vast cosmos remained completely hidden from their view. Only over the course of the past century has this grand, hidden architecture been slowly and breathtakingly revealed to us. Astronomers gradually learned that the countless stars we see are merely part of a single, sprawling spiral galaxy we call the Milky Way. And later still, they made the stunning discovery that our Milky Way is but one lonely island among hundreds of billions of galaxies scattered like dust across the boundless universe. Deep within the hearts of many of these distant galaxies lie sleeping giants, supermassive black holes of incomprehensible power. Some remain peacefully quiet and dormant, much like the gentle giant residing at the core of our own home galaxy, Sagittarius AR. Others, however, blaze with brilliant, terrifying light as active quasars, fueled when immense, swirling oceans of cosmic gas plunge helplessly toward their waiting abysses. 1 AU represents the average distance from our home planet to the Sun. 2618 represents one of the most extreme, awe-inspiring examples of this cosmic phenomenon ever witnessed. It stands as a humbling reminder that our universe harbors gargantuan structures operating on majestic physical scales far beyond anything we could ever hope to encounter in our brief, everyday lives. We speak of mind-bending black holes possessing the mass of tens of billions of our own suns. Superheated accretion disks that glow with a fierce brilliance far surpassing the combined light of entire, teeming galaxies. And terrifying event horizons wide enough to effortlessly swallow whole planetary systems in a single silent gulp. These staggering concepts can easily feel almost surreal, even dreamlike, when we first encounter them. Yet, the truly remarkable and beautiful thing is that they are not the products of wild speculation or empty imagination. They are the undeniable, elegant conclusions drawn from painstaking scientific observation and meticulous, patient measurement. For light, traveling tirelessly across the vast gulf of billions of years, acts as a cosmic messenger carrying precious, detailed information about the primordial structures that first gave it birth. By carefully studying this ancient, traveling light, modern astronomers can delicately reconstruct the physical properties of these incredibly distant quasars, estimate the immense masses of their central black holes, and map out the grand. Yet, despite this truly immense gulf, warm sunlight still reaches us with surprising swiftness, taking a mere 8 minutes to complete its long journey from the heart of the Sun to the surface of the Earth, unfolding history of cosmic evolution itself. Indeed, every single photon that gently collides with the mirror of a telescope on Earth carries with it a precious, tiny fragment of that epic, universal story. TS-618 is but one brilliant example among many astonishing discoveries that have so radically reshaped our humble understanding of the cosmos. Yet, it will always hold a profoundly special place in our imaginations because of its truly extraordinary, mind-defying scale. It sits majestically at the absolute upper limit of the black hole mass range currently known to human science. By studying its immense nature, astronomers can push the boundaries of knowledge, exploring the extreme limits of just how large these dark beasts can grow, and how rapidly they manage to feed in the early dawn of time. These passionate, tireless investigations continue to this very day. A new generation of advanced telescopes is constantly expanding our human vision, allowing us to peer deeper into the dark, velvety expanse of the distant universe. Exquisite instruments capable of detecting the faintest, longest wavelength infrared light can now peer back through the dusty corridors of cosmic history, revealing the very first galaxies and glowing quasars that illuminated the youthful universe. With every new observation, we stand on the precipice of discovery, waiting to uncover celestial objects even more colossal and awe-inspiring than any we currently know. So far, this cosmic ladder still feels somewhat graspable to our human minds. Somewhere out there, far beyond the dim, flickering reach of our current instruments, there may well be black holes far more gargantuan than TON 618. Or perhaps this titan, TON 618, already sits precariously close to the absolute natural limits imposed by the immutable laws of physics and the grand evolution of galaxies. Dedicated astronomers are still working tirelessly to answer that profound question. But even without knowing the final, ultimate answer, the mere existence of TON 618 already whispers something incredibly important to us. The universe is fully capable of building colossal structures on a scale far greater and more terrifying than our fragile, everyday intuition would ever dare suggest. And yet, these truly enormous structures remain intimately connected to the very same physical laws that quietly shape everything else in existence. Relentless gravity pulls cosmic matter together. Immense energy is violently released when that matter falls helplessly into deeper, darker gravitational wells. Both time and space respond fluidly to mass and motion, moving strictly according to the elegant rules described by general relativity. The moon remains a mere second away, while the sun stays a comfortable 8 minutes in the distance. From the silent collapse of a single star to the ravenous growth of a brilliant quasar billions of light-years away, the exact same fundamental principles apply. As you look up thoughtfully at the velvet night sky again, it is deeply worth remembering how much breathtaking complexity hides behind those small, twinkling points of light. Some of the friendly stars you see belong safely to our own home galaxy. Others may be incredibly distant galaxies whose ancient light has traveled for millions of weary years just to reach us. And far, far beyond what the limited naked eye can ever hope to detect lie gargantuan objects like TON 618, shining quietly yet brilliantly across unimaginable, icy distances. Their ancient light tirelessly continues traveling through the empty cold of space even now. Some of that wandering light may still be billions of years away from finally reaching the next advanced telescope that will patiently detect it. The universe does not rush its grand design. Its largest, most magnificent structures evolve with supreme patience across immense, unfathomable stretches of time. Stars softly form, burn brightly, and eventually fade away. But the very moment we venture beyond the quiet boundaries of our solar system, the numbers begin to expand with terrifying, breathtaking speed. Vast galaxies drift dreamily through space and occasionally, beautifully merge. Sovereign black holes grow, feed greedily, and sometimes inevitably fall silent. Through patient, careful observation, we have only just begun to comprehend a small, precious part of that vast, eternal story. And tonight, simply by following the incredibly faint, delicate trail of light from one distant, ancient quasar, we have taken a quiet, wondrous journey across billions of years and unimaginable, lonely distances, all the way from our beautifully small planet back to the silent, infinite sky stretching above us. The closest star system to our Earth is Alpha Centauri, whose brilliant light requires more than 4 long years to journey across the cold void to reach our eyes. This means that the shimmering light we perceive from that star tonight actually departed from its surface 4 years ago, traveling through the dark emptiness ever since. Faced with such dizzying distances, astronomers utilize another elegant measure called the light year. A light year is simply the immense distance that a beam of light travels in the span of one Earth year. Given that light races through the void at a blistering 300,000 kilometers per second, it covers an absolutely staggering amount of distance during that time. A single light year equals roughly 9.46 trillion kilometers. Already, our fragile minds are being gently pushed deep into unfamiliar, dizzying territory. Confronting trillions, numbers that stretch infinitely far beyond our ordinary, everyday experiences. And yet, the cosmic scale keeps relentlessly expanding. Our magnificent home, the Milky Way galaxy, spans a breathtaking 100,000 light-years from edge to edge. Nestled within its glowing spiral arms are hundreds of billions of stars, drifting alongside cosmic clouds of gas, swirling dust, countless planets, and many other wonderfully strange, mysterious objects. And sitting quietly at the very heart of this vast galaxy lies a supermassive black hole known as Sagittarius A star. As we touched upon earlier, this dark gravitational beast contains roughly 4 million times the mass of our own Sun. That may sound absolutely monstrous, and indeed it is, but when measured against the true, gargantuan giants of the cosmos, Sagittarius A star is actually quite modest, almost humble. T618, the silent cosmic titan we are slowly and carefully working our way toward tonight, exists on a scale far, far beyond such simple measurements. But before we return our gaze to that ultimate giant, let us pause for a quiet moment and contemplate something truly fascinating. When you look up at the velvet night sky, the stars appear deceptively scattered across a flat, two-dimensional surface, looking almost like tiny, sparkling jewels pinned to a dark, endless ceiling. Your human eyes cannot easily detect the profound, echoing depth of how far away they truly are. Some stars that appear to be cozy neighbors, resting close together in the night sky, are actually separated by hundreds or thousands of silent light-years in the cold depths of space. Other stars may appear faint and flickering, not because they are inherently small, but simply because they are positioned unimaginably far away in the dark abyss. This is perhaps one of the most profound reasons why astronomy is such an exceptionally patient science. To truly comprehend the vast scale of the cosmos requires meticulous measurement, tireless observation, and a humble willingness to completely rethink our deepest assumptions. For thousands of years, we humans naturally believed that our own Earth stood at the absolute center of everything. The radiant sun, the glowing moon, and the glittering stars all seemed to gracefully circle around us with each passing day. From the simple perspective of someone standing firmly on the ground, that intuitive explanation made perfect, undeniable sense. It wasn't until early astronomers began studying planetary motion in painstaking detail that the grand truth slowly and beautifully emerged. Earth is not the center of this boundless universe. It is not even the heart of our own solar system. And our solar system itself is merely one tiny, quiet region tucked inside a majestic galaxy that contains hundreds of billions of brilliant stars. Once that humbling realization settled in, scientists began to ask much deeper, more profound questions. If our home galaxy is so incredibly large, how many other galaxies might be drifting out there in the void? The answer, as it turns out, is truly staggering. Modern scientific observations suggest that the observable universe contains hundreds of billions of distinct galaxies. Each of these galaxies, in turn, may contain hundreds of billions of individual stars. That means the total number of shining stars in the observable universe could easily exceed the countless grains of sand resting on all the sun-drenched beaches of the Earth. And among those infinite stars and swirling galaxies, mysterious black holes appear to be surprisingly, almost shockingly common. Some of these cosmic chasms are relatively small, violently formed when massive, dying stars collapse inward at the very end of their lives. Others are vastly larger, sitting quietly and monolithically at the deep centers of galaxies, effortlessly influencing the orbital motion of billions of surrounding stars. But every once in a while, astronomers discover something so extraordinary that it pushes the absolute limits of what they ever expected to find. Celestial objects that seem almost impossibly large, almost too violently energetic to exist. Tun 618 is precisely one of those breathtaking discoveries. It exists at a staggering distance of more than 10 billion light-years from Earth. This means the faint light we observe from it tonight actually began its lonely journey across the cold expanse of space when the universe was far younger and more turbulent than it is today. Back then, primitive galaxies were still actively forming, and newborn stars were still being slowly assembled from vast, glowing clouds of interstellar gas. And somehow, in that ancient, primordial cosmic environment, a monstrous black hole began growing into one of the largest, most formidable objects of its kind that humanity has ever measured. But to truly appreciate just how extraordinary that rapid growth is, we must pause to think carefully about scale once again. This is because black holes behave in ways that are radically different from most objects we encounter in our everyday lives. If you double the physical mass of a simple rock, its size does not increase in any dramatic, noticeable way. If you double the mass of a planet, its diameter may grow only slightly, but certainly not enormously. Black holes, however, follow a much more direct and elegant relationship between mass and physical size. As their immense mass increases, the radius of their mysterious event horizon increases in a perfectly predictable way. In other words, a heavier black hole is also physically, geometrically larger. That means when we say ton 618 contains tens of billions of solar masses, we are not merely talking about an unimaginable weight. We are also describing a colossal event horizon that stretches across a vast, staggering region of space. A definitive boundary where the pull of gravity becomes so overwhelmingly strong that not even light itself can escape. This silent boundary defines the true, physical size of a black hole. And in the unique case of ton 618, that size becomes almost impossibly difficult for the human mind to fully comprehend. Imagine drawing a definitive circle around an object, where crossing that threshold means there is no possible path back out again. No powerful rocket could ever escape. No swift beam of light could ever return. Absolutely everything that crosses that invisible boundary becomes permanently, eternally trapped. For a relatively small stellar black hole, that fatal circle might span only a few dozen kilometers across. For the supermassive black hole resting at the silent center of our own galaxy, it spans tens of millions of kilometers. For ton 618, however, that titanic circle expands to a gargantuan scale that almost audaciously begins to compete with the vast dimensions of entire planetary systems. To truly picture something of this magnitude can feel utterly surreal, testing the very limits of our imagination. Our own familiar solar system is itself a staggeringly immense expanse. The annual orbit of Earth around our life-giving sun covers nearly 1 billion quiet kilometers each year. Even the distant orbit of Neptune, the outermost major planet of our system, lies billions of lonely kilometers away from the sun's warm embrace. And yet, the monstrous event horizon of ton 618 would stretch effortlessly across a cosmic region large enough to completely swallow a significant portion of that monumental space. We will explore these staggering comparisons with careful contemplation as we move forward, for they gently help translate cold, abstract numbers into something deeply tangible to the human spirit. But the quiet majesty of the night sky offers us another profound clue about this scale, one that is deeply worth considering. Every tiny point of light we gaze upon represents a preserved moment in the distant past. Because light takes time to travel across the great void, looking deeper into the cosmos also means gazing further back in time. The gentle moon appears to us as it was just one fleeting second ago. The radiant sun appears as it was 8 minutes ago. The nearest stars appear as they shone years ago, while unimaginably distant galaxies appear as they were millions or even billions of years in the past. Ton 618 belongs entirely to this ancient, whispering past. When its ancient light first began its epic journey toward Earth, our home planet was already billions of years old. Yet, the dawn of human civilization had not even begun to flicker. In fact, complex life on land was still slowly and hesitantly evolving. The mighty dinosaurs had long since vanished into the shadows of time, and early mammals were only gradually spreading across the silent continents. Over the billions of years that quietly followed, life on Earth transformed dramatically. Continents slowly drifted across the globe, and great ice ages came and went like seasonal breaths. Eventually, curious humans began looking up at the dark sky, wondering what those distant, shimmering lights might truly be. Now, equipped with modern telescopes and meticulous analysis, we can gracefully detect objects like ton 618, even though they exist unimaginably far away in the dark. This profound ability to measure and comprehend such distant things remains one of the most remarkable and poetic achievements of human science. Yet, It also gently leads us back to the haunting question that quietly sits at the center of tonight's exploration. If Ton 618 truly contains tens of billions of solar masses, if it dynamically powers one of the brightest quasars in the known universe, if it sits billions of light-years away in a young, turbulent galaxy, then just how unfathomably large must its event horizon actually be? When people first hear the cold name of Ton 618, it does not immediately sound like anything familiar or comforting. It possesses no poetic name like Andromeda or Orion, nor even a vividly descriptive title like the Crab Nebula. Instead, it sounds rather clinical, like a mere catalog number. And indeed, that is exactly what it is. Ton 618 is the designation given to a cosmic object listed in a vast catalog of astronomical observations. The TON prefix originates from the Ton-Ant-Zintler Observatory in Mexico, where dedicated astronomers compiled a catalog of unusual, bright blue stellar objects many decades ago. These particular objects stood out because they appeared extremely bright and energetic when viewed through early telescopes. At that time, no one could have possibly known that some of these strange, flickering points of light would later turn out to be among the most unimaginably powerful objects in the entire universe. Ton 618 was simply one quiet entry in that dusty catalog, just a tiny, distant point of light captured on fragile photographic plates. But as our telescopes steadily improved and astronomers began studying it with deeper curiosity, something truly remarkable became clear. Ton 618 was not a star at all. It was something infinitely stranger. To truly comprehend what Ton 618 really is, we must step into a breathtaking category of objects known as quasars. A quasar is one of the most brilliantly luminous things the cosmos can ever produce. In fact, a single solitary quasar can shine far more brightly than an entire grand galaxy containing hundreds of billions of stars. That might sound almost impossible to our limited minds at first. After all, galaxies are colossal, majestic collections of stars, swirling gas, cosmic dust, and mysterious dark matter. The mere idea that a single, compact object could completely outshine an entire galaxy seems almost absurdly impossible. And yet, quasars do precisely that. The reason is that the light we observe from a brilliant quasar does not actually originate from a burning star. Instead, it emanates from the chaotic, highly energetic environment immediately surrounding an incredibly supermassive black hole. Now, black holes themselves do not emit any light at all. Indeed, they are aptly named black holes precisely because their immense gravity traps all light, never allowing it to escape or release back into the cosmos. Yet, the doomed material swirling directly around a black hole can become blindingly, phenomenally bright. Wandering gas, cosmic dust, and other remnants of matter falling helplessly toward a black hole rarely plunge straight into its abyss. Instead, they gracefully form a rapidly rotating disk of superheated material around it. This colossal, glowing structure is known to science as an accretion disk. One can easily imagine it somewhat like water spiraling relentlessly down a household drain, except on a vastly, unimaginably larger scale. As this helpless matter spirals ever closer inward, gravity relentlessly squeezes it tightly, forcing it to move faster and faster at dizzying speeds. The violent friction between colliding particles heats the spiraling material to truly extraordinary temperatures, climbing to millions of degrees. At these unimaginable temperatures, the highly agitated gas begins to glow intensely, producing enormous, staggering amounts of radiation across many different wavelengths of light. Consequently, that glowing disk becomes brightly visible across almost incredible cosmic distances. And when a gargantuan black hole is actively, voraciously feeding on these large amounts of stellar matter, the brilliant light from the surrounding disk can become so breathtakingly powerful that we observe it across the void as a quasar. T618 is one of those majestic quasars. But it is not just any ordinary quasar. It stands proudly among the most luminous quasars ever observed in the entire history of astronomy. From our distant home on Earth, this titanic object appears only as a faint, unassuming point of light. Even through a modern telescope, it does not look especially dramatic or imposing. Yet, that single, whispering faint dot represents something utterly extraordinary. The ancient light from Tun 618 has traveled through the cold void for more than 10 billion years to reach our eyes. That means when the very light we see tonight first left its distant source, the universe itself was much younger, still in its energetic infancy. Ancient galaxies were still actively evolving, and newborn stars were forming rapidly and brightly across the vast cosmos. The familiar, large-scale structures we observe today were only just beginning to take their grand shape. Deep somewhere inside one of those distant, primordial galaxies, a monstrous black hole was growing at a truly astonishing rate. And that silent black hole is the mighty engine actively powering the brilliant quasar we now call to N618. When dedicated astronomers carefully analyzed the incoming light from this distant object, they noticed something highly unusual about the turbulent gas surrounding it. The gas was moving extremely fast, whipped into a frenzy. In fact, it was moving so incredibly quickly that the only reasonable, scientifically sound explanation was the invisible presence of an incredibly massive black hole pulling violently on it. Using a sophisticated technique called spectral analysis, patient scientists studied the light from the distant quasar in great, meticulous detail. When cosmic gas moves so rapidly, the delicate light it emits becomes either stretched or compressed in subtle, measurable ways. By carefully analyzing these minute changes, astronomers can precisely estimate how fast the gas is orbiting the central, hidden object. And when they ultimately calculated those extreme speeds, they arrived at a truly astonishing, mind-bending conclusion. The colossal black hole at the dark center of Tun 618 contains tens of billions of times the mass of our own Sun. Current scientific estimates place it at roughly 66 billion solar masses. That unfathomable number alone proudly places it among the absolute most massive black holes ever measured in the cosmos. To put that overwhelming figure into a clearer context, let us briefly revisit the familiar black hole resting at the quiet center of our own galaxy. Sagittarius A star contains about 4 million solar masses, which already sounds incredibly large to our human minds. Yet, the monstrous Tun 618 outweighs it by more than a staggering 16,000 times. Another famously massive, supermassive black hole sits quietly in the dark center of the giant galaxy Messier 87. This iconic black hole, which was historically photographed by the Event Horizon Telescope in 2019, contains around 6.5 billion solar masses. At the time, that was widely considered an extraordinary, terrifying example of a massive black hole. But the giant Tun 618 is roughly 10 times more massive even than that. Numbers like these inevitably begin to stretch our fragile human imagination in deeply unusual ways. They are so overwhelmingly large that they almost stop feeling meaningful to us. That is why thoughtful astronomers often try to translate these abstract values into physical, tangible size. Because, in truth, the sheer mass of a black hole directly determines the exact physical size of its dramatic event horizon. This event horizon is the ultimate, inescapable boundary around a black hole where escape becomes utterly impossible. If you were to cross that invisible boundary, the relentless pull of gravity would become so profoundly overwhelming that no conceivable amount of energy could ever carry you back to the warm light of the living universe. Even the swiftest light itself cannot escape. For smaller, more modest black holes, this fateful boundary can be surprisingly, almost deceptively, small. A stellar black hole containing roughly 10 times the mass of our Sun might possess an event horizon spanning only about 60 kilometers across. That is a span smaller than many sprawling cities on Earth. Yet, the immense gravitational pull at that narrow boundary would still be completely overwhelming. As the mass of a black hole increases, its event horizon expands in perfect, direct proportion. Double the concentrated mass, and the dark radius doubles. Increase that mass 1,000-fold, and the radius increases by 1,000-fold as well. This beautifully simple relationship makes it possible for astronomers to estimate the colossal size of extremely massive black holes, such as the one in 618. And when dedicated astronomers run those profound calculations, the resulting numbers are nothing short of astonishing. The event horizon of Tun 618 is estimated to span hundreds of billions of kilometers. To offer our fragile minds some much-needed perspective on this scale, consider the lonely, distant orbit of Neptune, the outermost major planet in our solar system. Neptune silently travels around the Sun at an immense average distance of about 4.5 billion kilometers. That is already a breathtakingly vast distance. Yet, TON 618's event horizon is so incomprehensibly enormous that it could easily and effortlessly swallow the entire region inside Neptune's orbit many times over. If our Sun was somehow replaced by this monstrous black hole, much of our familiar solar system would lie well inside that absolute point of no return. But to 618's gargantuan influence does not simply stop at its dark event horizon. Far beyond that abyssal boundary lies a vast, turbulent region completely dominated by its relentless gravity. Cosmic matter captured in this region can form enormous, glowing accretion disks stretching across unimaginable distances comparable to the size of entire planetary systems. Powerful jets of energy can also violently erupt from the highly charged regions surrounding the black hole, blasting fierce radiation deep into the cold void of intergalactic space. These highly energetic, dramatic processes are precisely what make quasars visible from such incredible ancient distances. Without the brilliant, glowing accretion disk surrounding TON 618, we might have lived in eternal ignorance, never knowing it existed at all. The dark heart of the black hole itself remains completely invisible. What we actually see is the chaotic, beautifully glowing environment frantically swirling around it. And even that luminous environment lies countless billions of light-years away from our quiet corner of space. At such unfathomable distances, individual, minute details become utterly impossible to observe directly. Instead, patient astronomers must rely on exceptionally careful measurements of faint light and subtle motion to piece together the cosmic drama of what is happening. It is a bit like standing in the dark, listening to the low rumble of distant thunder, and using that solitary sound to estimate the vast size of the oncoming storm. You cannot see every dark detail of the swirling clouds, but you can still learn a surprising, deeply rewarding amount about what is happening inside them. T618 represents one of the most extreme, captivating examples of this kind of cosmic detective work. A mere, faint point of light in the velvet night sky turned out to be powered by a central black hole so massively colossal that it profoundly challenges our fundamental understanding of how such celestial objects grow. And that naturally raises a highly interesting, lingering question. How does something so unimaginably grand become so incredibly large? Black holes usually grow in two primary, well-documented ways. They can greedily swallow nearby gas and cosmic dust, gradually accumulating more mass over vast stretches of time. Or, they can violently merge with other black holes when entire galaxies collide in cosmic dances. Over billions of slow years, these relentless processes can create very large, dominant black holes residing at the ancient centers of galaxies. But reaching a staggering scale of tens of billions of solar masses is still exceptionally difficult for science to explain. TON 618 strongly suggests that in the mysterious early universe, some primitive black holes may have grown much faster, and far more aggressively, than we once believed possible. Perhaps they originally formed from unusually massive primordial seeds. Perhaps they greedily consumed truly enormous, dense amounts of matter in the extremely crowded young galaxies of the early epoch. Or, perhaps, there are profound growth mechanisms operating out there that we still do not fully, truly understand. Astronomers are still actively and eagerly investigating these fascinating possibilities today. But for the quiet purpose of our wondrous journey tonight, the single most important thing to remember is this. TON 618 is not simply a black hole. It is the central engine of a powerful quasar, a colossal cosmic furnace fueled entirely by the relentless pull of gravity, a chaotic yet beautiful region of deep space where unimaginable torrents of cosmic matter spiral endlessly inward, heating to unfathomably high temperatures and releasing brilliant, piercing light that travels tirelessly across billions of years of cosmic history. And at the very heart of all this violent, luminous activity lies a silent, gravitational boundary so incredibly vast that its true physical scale is almost impossible for us to comprehend at first. To understand this, try picturing something quite simple for a brief moment. Imagine yourself standing quietly beside a familiar, comforting object, something you see almost daily in your ordinary life, perhaps a modest house or a quiet car parked along a peaceful, tree-lined street. These are humble objects with physical dimensions our human minds can comprehend with ease. A car might stretch a simple 4 or 5 meters long, while a cozy house might span 10 or 15 meters across. Even the grander structures of our world's schools, bustling offices, and soaring stadiums still remain comfortably within a tangible scale that feels completely manageable to our senses. Your brain has quietly spent your entire life learning how to effortlessly navigate and interpret physical sizes like these. If someone tells you that a certain building is twice as large as another, you can vividly picture that comparison in your mind's eye without any real strain. If someone describes a majestic mountain as being 3 times taller than a neighboring peak, the grand image still makes intuitive sense. The simple numbers remain beautifully connected to our lived, earthly experiences. But this warm, comfortable sense of scale begins to tremble and weaken the very moment we turn our eyes upward toward the endless night sky. Earlier, we softly mentioned that Tons 618 harbors a staggering 66 billion times the mass of our own sun. That immense number alone is already deeply difficult for the human mind to fully process. This struggle arises not because the mathematics are mathematically complicated, but because our earthbound intuition is simply not designed to grasp values of such staggering magnitude. And the very moment we attempt to convert that unimaginable mass into a physical, spatial size, this quiet difficulty becomes even more pronounced. Our human intuition naturally works best when it can gently compare things belonging to the same general, familiar category. For instance, we easily grasp the difference between a peaceful, small lake and a vast, sweeping lake, or between a quiet, small town and a sprawling, energetic city. Even when the contrast between them is highly dramatic, the underlying comparison still feels grounded and entirely reasonable. But the strange, silent objects of the cosmos do not always behave in such a familiar, comforting way. When black holes grow larger, their physical boundaries expand in a remarkably straightforward, direct manner. The mathematical relationship between their mass and their radius is almost perfectly proportional. This elegant rule means that if one black hole is 10 times more massive than another, its dark event horizon will also be exactly 10 times larger. Though that rule sounds wonderfully simple on paper, when we apply it to a celestial titan like Tun 618, the physical consequences become utterly extraordinary. Let us begin our mental journey with a much smaller, gentler example to build our intuition slowly. Suppose, for a moment, we examine a hypothetical black hole possessing the exact same mass as our warm sun. If our great sun were somehow compressed into a dense, dark black hole, its boundary, the event horizon, would span a mere 3 kilometers across. This means that the entire immense mass of the sun, which is over 300,000 times the mass of our Earth, would be tightly squeezed into a tiny, silent sphere roughly the size of a modest countryside town. That image might already sound quite surprising to our ears. After all, the sun is a truly enormous beacon, its bright diameter stretching roughly 1.4 million kilometers across. Yet, transformed into a black hole, it would shrink down to a dark sphere barely a few kilometers wide. Now, let us imagine a slightly larger black hole, one with 10 times the mass of our sun. According to that same proportional rule, its event horizon would expand to about 30 kilometers across. Even so, it remains remarkably small by our everyday standards. If you were to place it gently somewhere on Earth, it would fit quite comfortably inside the borders of a single large metropolitan area. But these stellar black holes are merely the smallest, most modest members of this mysterious cosmic family. As dedicated astronomers began looking deeper and studying the silent centers of distant galaxies, they discovered something far more impressive and awe-inspiring. Deep at the heart of many galaxies lies a supermassive black hole, an ancient giant harboring the weight of millions, or even billions, of solar masses. Our own celestial home, the Milky Way galaxy, provides a beautiful and useful example of this phenomenon. Sagittarius, a star, the quiet black hole residing at the very center of our galaxy, contains about 4 million times the mass of our sun. When we apply that very same proportional rule, its invisible event horizon expands dramatically to roughly 24 million kilometers across. That staggering distance is already enormous indeed. For comparison, the physical diameter of our own life-giving sun is roughly 1.4 million kilometers. This means that the invisible, yawning event horizon of Sagittarius A star is more than 17 times wider than the sun itself. If this dark colossus were to suddenly replace the sun at the heart of our solar system, the absolute boundary where gravity seals all doors and escape becomes forever impossible would extend nearly halfway to the scorched orbit of Mercury. Already, these staggering numbers begin to strain and stretch the limits of our fragile human imagination. Yet, the cosmic titan known as TON 618 exists in an entirely different, almost unfathomable category. Instead of mere millions of solar masses, this ancient leviathan harbors tens of billions. And because the physical size of a black hole scales in direct, unwavering proportion with its massive weight, its terrifying event horizon expands outward accordingly. Astronomers carefully estimate that the shadow-swept event horizon of TON 618 boasts an astronomical radius of roughly 195 billion kilometers. Consequently, the colossal diameter stretching from one distant edge of this cosmic abyss to the other would measure nearly 390 billion kilometers. These gargantuan figures are so profoundly immense that they almost cease to carry any real meaning for us, unless we gently anchor them to something deeply familiar. One highly illuminating comparison involves the structured layout of our very own solar system. The innermost planet, Mercury, orbits at a distance of about 58 million kilometers from the Sun. Radiant Venus journeys along its path at around 108 million kilometers, while our precious Earth orbits at a comfortable 150 million kilometers. Even the icy orbit of Neptune, the outermost major planet of our system, lies roughly 4.5 billion kilometers away from the solar center. Yet, when we boldly place the vast expanse of TON 618's event horizon beside these grand celestial distances, something truly breathtaking and remarkable appears. The dark boundary of the event horizon alone would extend far, far beyond the lonely orbit of Neptune. Indeed, it would reach several times farther into the cold dark than even the most distant of our outer planets. Picture, if you will, replacing our central sun with T618. Mercury, Venus, Earth, and Mars would not merely find themselves orbiting closer to the dark void. Rather, they would instantly lie deep within the shadowy realm where escape is utterly impossible. The exact same grim fate would await majestic Jupiter and ringed Saturn. Even Neptune, which feels so incredibly far from our warm sun, would be instantly swallowed whole by this unyielding event horizon. Only the most distant, frozen icy objects residing at the outermost fringes of our solar system might barely remain outside that dark, inescapable boundary. For many of us, this is the precise moment where human intuition begins to falter and fail. Our solar system already feels incomprehensibly vast to our earthly senses. Robotic space probes launched from Earth must journey for many silent years just to reach the outer planets. The legendary Voyager spacecraft, which departed our blue world in the hopeful decade of the 1970s, have been traveling tirelessly for nearly half a century, and are only now gently touching the outermost edge of the Sun's magnetic influence. Yet, the silent event horizon of TON 618 alone would effortlessly engulf a cosmic region far larger than that entire planetary neighborhood. And we must remember that this is merely the threshold where escape becomes impossible. The invisible gravitational dominion of this black hole reaches out immeasurably far beyond that boundary. Swirling matter orbiting safely outside the event horizon can still journey along stable paths, gradually weaving together enormous, glowing disks of superheated gas and cosmic dust. These majestic accretion disks can span distances far greater and more sweeping than the event horizon itself. In the spectacular case of powerful quasars like the 618, this swirling accretion disk transforms into one of the most brilliantly luminous structures in the entire known universe. As gas spirals helplessly toward the central abyss, it heats up dramatically, shedding vast amounts of energy as it plunges inward. Temperatures climb to scorching millions of degrees, unleashing intense radiation across the entire electromagnetic spectrum. The breathtaking result is a radiant, luminous beacon shining brightly across the cosmos, visible from billions of light-years away. All of this violent, beautiful activity unfolds within a vast region utterly dominated by the supreme gravity of the central black hole. And as the black hole grows ever more massive, so too does this colossal surrounding environment expand. Another profound way to contemplate the unimaginable scale of Tun 618 is to compare its majestic size with other famous black holes that astronomers have carefully studied. In the historic year of 2019, scientists successfully captured the very first image of a black hole's dark shadow using the Event Horizon Telescope. The awe-inspiring object featured in that historic image was the supermassive black hole residing at the heart of the giant elliptical galaxy Messier 87. That colossal black hole contains about 6.5 billion solar masses. At the time, it was widely celebrated as one of the largest black holes ever measured by humanity. Yet, the mighty TON 618 is roughly 10 times more massive than even that towering giant. If you could somehow place both of these monstrous objects side by side, the event horizon of TON 618 would utterly dwarf the one residing in the heart of Messier 87. Yet, beyond this unimaginable scale, there lies something far more profoundly fascinating about these colossal cosmic giants. Their immense event horizons are not merely larger. They are, in a strangely beautiful sense, much gentler. Around smaller, stellar mass black holes, the sheer gravitational variance between your head and your feet would be terrifyingly immense. This violent differential, scientifically known as the tidal force, would ruthlessly stretch any approaching object into an impossibly long strand, a dramatic and destructive phenomenon aptly described by astronomers as spaghettification. For those smaller, stellar mass black holes, this devastating stretching would tear you apart long before you ever reached the safety of the event horizon. Yet, for an ultramassive titan like TON 618, the event horizon lies so incredibly far from the central singularity that the destructive tidal forces near this dark threshold are surprisingly weak. In theory, a traveler gently crossing the event horizon of such a colossal entity might not perceive anything unusual at that precise, fateful moment. There would be no tangible surface to strike, no violent, sudden impact, but rather a serene, quiet transition into a silent realm from which escape is forever impossible. To an outside observer, however, the falling traveler would appear to gradually slow down and softly fade away as they neared the event horizon. The light they emitted would be stretched into longer, redder wavelengths, growing progressively dimmer until it finally vanished altogether into the eternal dark. This deeply mysterious behavior stems directly from the profound ways in which intense gravity warps both time and light near these ultramassive cosmic abysses. It is precisely one of the many reasons why black holes remain such endlessly captivating subjects of modern astrophysics. TON 618 takes these surreal concepts and boldly pushes them to the absolute limits of what we can currently observe in our vast universe. Its unfathomable mass creates a gravitational boundary far larger than our entire solar system. Its violently churning accretion disk radiates enough brilliant energy to completely outshine the host galaxy that cradles it. And the light we see today has journeyed across more than 10 billion years of cosmic history just to whisper its secrets to our telescopes. Yet, despite this staggering, mind-boggling scale, when astronomers peer at TON 618 through their instruments, it still appears only as a microscopic point of light, a solitary, faint speck against the velvet canvas of the night. This striking contrast between deceptive appearance and grand reality remains one of the most breathtaking wonders of astronomy. The cosmos whispers its greatest secrets in silence, hiding its most colossal structures behind distances so incredibly vast that they shrink to almost nothingness from our humble perspective. Yet, through meticulous measurement and deeply patient observation, dedicated scientists can gradually unveil the grand truths that these distant, shimmering specks represent. And when we begin to translate those incomprehensible numbers into familiar, tangible comparisons, comparing them to our own solar system, the wide planetary orbits, and distances measured in billions of kilometers, the true, majestic scale of the universe slowly starts to come into focus. TON 618 is far from being just another exceptionally large black hole. It embodies a staggering level of cosmic growth that profoundly challenges our current understanding of how these primordial monsters first formed and evolved over eons. At a passing glance, it might indeed seem utterly impossible to measure something that is intrinsically invisible. When an object neither emits nor reflects a single photon of light and lies cradled billions of light-years away, the scientific challenge begins to sound almost entirely hopeless. After all, our ordinary, everyday experience with measuring the world relies almost entirely on our ability to see things clearly. We can effortlessly measure the simple length of a wooden table with a standard ruler, the soaring height of a grand building with precise surveying tools, or the distance to a rolling green hill with a modern laser rangefinder. Every single one of these common methods rests upon a fundamental, comforting principle: the ability to observe our subject directly. Black holes, however, completely strip away this possibility. By their very dark nature, they mercilessly trap light. Any wandering photon that crosses the threshold of the event horizon can never hope to escape again. This means that the defining, fateful boundary of a black hole, the event horizon itself, remains perpetually invisible to even our most advanced telescopes. Thus, the intriguing question naturally arises: how do astronomers measure an object that cannot be seen at all? The answer is both elegant and surprisingly clever. Instead of futilely trying to observe the dark abyss directly, scientists carefully study everything swirling in its immediate vicinity. The volatile space surrounding a black hole is rarely ever empty. Vast clouds of gas, glowing dust, and sometimes even entire wandering stars can orbit nearby. These celestial objects move gracefully under the immense influence of gravity, and their dynamic motion can ultimately reveal a great deal about the massive, invisible entity lurking at the center. Gravity, in this profound sense, leaves its own distinct fingerprints. When any object journeys through the silent void of space under the heavy influence of gravity, its precise speed and direction depend entirely on how relentlessly strong that gravitational pull is. By carefully and patiently measuring those subtle motions, astronomers can work backward to calculate the exact mass responsible for this cosmic choreography. This elegant method has been used successfully many times in the history of astronomy. In fact, it was employed long before the mysterious concept of black holes was ever conceived. In the mid-19th century, vigilant astronomers noticed that the distant planet Uranus was not moving exactly in the way they expected. Its celestial orbit contained small, perplexing irregularities that could not be adequately explained by the gravitational influence of the known planets. Instead of simply dismissing this annoying problem, curious scientists investigated further. They gradually realized that this strange, erratic motion might be caused by another unseen, distant planet pulling gently on Uranus from even farther out in the cold solar system. Using the pure power of mathematics alone, they confidently predicted where that hidden planet should be located. Soon afterward, powerful telescopes were pointed eagerly toward the predicted coordinates, and the majestic planet Neptune was discovered almost exactly where the mathematical calculations suggested it would be. This brilliant kind of reasoning, inferring the existence of a completely invisible object from its gravitational influence, became an incredibly powerful tool in astronomy. Similarly, black holes are discovered and measured using this exact, clever approach. In the specific case of the cosmic giant Tun 618, astronomers did not see the black hole itself directly. What they observed instead was the extremely bright, blazing quasar produced by the superheated matter swirling violently around it. As gas spirally descends toward the black hole, it gradually forms the glowing accretion disk we discussed earlier. This rotating disk becomes incredibly hot, emitting truly enormous amounts of energetic radiation across the vast electromagnetic spectrum. Modern telescopes can capture this faint radiation and carefully spread it into a detailed spectrum, separating the different wavelengths of light, much like a simple glass prism beautifully separates ordinary sunlight into a colorful rainbow. Deep inside that detailed spectrum, astronomers eagerly look for specific, telltale patterns called emission lines. These distinct lines originate directly from excited atoms in the turbulent gas surrounding the black hole. When these atoms absorb or release energy, they produce vibrant light at very particular wavelengths. Hydrogen, helium, carbon, and many other elements each have their own uniquely recognizable signatures, like a cosmic chemical barcode. But there is a crucial, fascinating detail hidden deep within those faint lines. If the gas emitting the light is moving rapidly, the cosmic wavelengths shift ever so slightly. This physical effect is widely known as the Doppler shift. You might already be familiar with this phenomenon in your everyday life. When an ambulance rushes past with its loud siren on, the pitch of the sound dramatically changes as it moves quickly toward you and then rapidly away from you. The sound waves are tightly compressed as the ambulance approaches and stretched out as it moves away. Remarkably, light behaves in a very similar way. When glowing gas moves toward us, its emitted light shifts slightly towards shorter, higher frequency wavelengths, appearing distinctly bluer. When it moves away, the light stretches toward longer wavelengths, appearing noticeably redder. By precisely measuring these tiny, subtle shifts in the emission lines, astronomers can accurately determine exactly how fast the gas is moving. And near a truly massive black hole, the swirling gas can move incredibly, breathtakingly fast. In the extraordinary case of Tun 618, the gas within the quasar's broadline region, a turbulent area close to the black hole, was observed moving at speeds of thousands of km/s. Such enormous, mind-boggling speeds immediately suggest the presence of an incredibly powerful gravitational force. But diligent astronomers do not stop there. Once the speed of the gas is known, the next crucial step is to estimate how far that gas is situated from the central black hole. This cosmic distance is far more difficult to determine directly, but scientists employ several clever, indirect techniques. One of them involves carefully observing how the overall brightness of the quasar changes over time. Quasars, you see, are not perfectly steady, static sources of light. The dazzling brightness of the swirling accretion disk can fluctuate dynamically as cosmic gas spiraling inward is eagerly consumed, releasing tremendous torrents of raw energy. These luminous fluctuations then propagate outward like ripples in a pond, traveling slowly through the vast, surrounding clouds of gas. By meticulously measuring the subtle time delay between the sudden changes in this central brightness and the corresponding response in the emission lines produced by the outer gas, astronomers can skillfully estimate the immense distance separating these two cosmic regions. This elegant, indirect method is known in the scientific community as reverberation mapping. It works beautifully, much like shouting into the depths of a colossal, quiet canyon and listening intently for the returning echo. The fleeting delay between the initial shout and the returning echo clearly reveals just how far away the ancient canyon walls stand. In a remarkably similar way, the temporal delay between the fluctuating brightness of the quasar and the subsequent shifts in its emission lines reveals precisely how far the rapidly orbiting gas lies from the massive, central black hole. Once both the swift speed of the swirling gas and its vast distance from the center are accurately determined, astronomers can confidently apply the fundamental laws of gravity to estimate the staggering mass of the unseen object causing that grand orbital motion. This elegant calculation is fundamentally similar to the classic methods used to determine the mass of our own sun by closely studying the orderly motion of its planets. Planets orbit the sun because they are bound by its relentless gravitational pull. Thus, the faster a planet moves, or the closer it orbits to the solar surface, the stronger that guiding gravitational force must be. Vast clouds of gas orbiting near a supermassive black hole obey these exact same, universal physical rules. For to 618, these precise measurements recently revealed something truly extraordinary. The surrounding gas was found to be moving so incredibly quickly, and at distances so phenomenally large, that the gravitational mass required to govern such wild motion had to be tens of billions of times the mass of our own sun. No ordinary celestial object could ever produce such a colossal, mind-bending effect. Only an ultramassive black hole of mythical proportions could adequately explain these profound observations. Once this astronomical mass is finally known, determining the actual size of the mysterious event horizon becomes a relatively straightforward mathematical endeavor. Black holes obey a surprisingly simple mathematical relationship known as the Schwartz radius. This theoretical radius defines the boundary of the event horizon for a non-rotating black hole. The underlying formula itself is wonderfully elegant. For every single solar mass compressed within the heart of a black hole, the radius of its inescapable event horizon increases by approximately 3 kilometers. This means a hypothetical black hole with the exact mass of our Sun would possess an event horizon radius of only about 3 kilometers. A much larger black hole containing 10 solar masses would have a radius of about 30 kilometers, while a monstrous black hole with 1 million solar masses would boast a radius of roughly 3 million kilometers. This cosmic scaling continues smoothly and predictably as the gravitational mass grows ever larger. When we apply this direct relationship to the Titanic Tun 618, with its astonishing estimated mass of 66 billion solar masses, the resulting event horizon becomes unbelievably enormous. Its boundary radius reaches a staggering 195 billion kilometers, a majestic distance that stretches far, far beyond the lonely orbit of Neptune in our own solar system. Yet, even this immense, chilling calculation represents only the absolute threshold of no return, the dark boundary where physical escape becomes entirely impossible. The surrounding cosmic territory dominated by the black hole's intense gravity extends much, much farther into the deep void. Within this chaotic domain, gas organizes into colossal, rapidly rotating structures, and intensely powerful jets of raw energy can violently erupt from the poles of the glowing accretion disk. These magnificent jets are capable of stretching across unimaginable distances, growing larger than entire neighboring galaxies. All of this turbulent cosmic activity provides precious observational clues that modern astronomers can diligently analyze from afar. Even though the black hole itself remains eternally invisible, shrouded in absolute darkness, its powerful gravitational presence profoundly shapes and controls everything in its cosmic neighborhood. This brilliant concept, studying invisible, silent objects solely through their profound physical influence on their surroundings, stands as one of the most powerful and transformative methods in modern astrophysics. It allows curious scientists to fearlessly explore deep, hidden parts of the universe that can never be observed directly with traditional light. Mysterious dark matter, for example, is only detected through its silent gravitational effects on spinning galaxies, and distant exoplanets are often discovered by carefully observing the tiny, rhythmic wobbles they cause in the parent stars they orbit. Black holes follow this very same beautiful pattern. We may never directly gaze upon the event horizon of objects as unimaginably distant as to 618, but we can still confidently measure the immense mass and complex behavior of this unseen colossus through the frantic motion of the glowing matter swirling around it. In a poetic way, the silent black hole clearly reveals its hidden existence through the violent disturbances it creates in the fabric of space. Gas accelerates, light shifts, and vibrant energy radiates outward across the vast, silent chasms of billions of light years. By meticulously and patiently studying these faint, ancient cosmic signals, astronomers slowly and methodically assemble a vivid picture of the colossal, hidden giant lurking at the very center of this cosmic storm. TO 618 represents one of the most extreme, awe-inspiring examples of this profound investigative process. From a mere, faint speck of pale light shimmering in a profoundly distant galaxy, modern scientists have gradually inferred the staggering presence of a supermassive black hole so unimaginably immense that its event horizon alone would easily dwarf our entire planetary system. Yet, the remarkable, winding story of how this monstrous celestial object was first identified begins much earlier, long before its true, terrifying scale was ever conceived or understood. Decades ago, when pioneering astronomers first noticed this highly unusual, solitary point of light suspended in the deep velvet of the night sky, they had absolutely no inkling that they were gazing directly at one of the most monstrously massive black holes known to exist in the entire observable universe. Indeed, long before astronomers could even begin to comprehend what TO 618 truly was, it presented itself as something far less dramatic, almost humble in its quiet appearance. To the dedicated observers who first painstakingly recorded it, the object seemed to be nothing more than a faint, minuscule blue point of light captured on a fragile photographic plate. It did not immediately or loudly announce itself as a gargantuan black hole or a fiercely powerful quasar. Instead, it blended quietly and seamlessly among countless other distant, glittering objects scattered randomly across the vast celestial dome. This grand scientific journey begins in the vibrant middle of the 20th century, during a transformative period when the field of astronomy was changing with breathtaking rapidity. For long, quiet centuries, astronomers had relied almost exclusively on direct visual observations through classical telescopes. They would peer intently through the cold glass eyepiece, carefully sketch the delicate details of what they saw, and manually record the precise coordinates of stars and planets. But by the early decades of the 1900s, revolutionary photographic technology had utterly transformed the way the night sky was studied. Instead of relying solely on the fallible and fleeting nature of human eyesight, astronomers could now permanently capture vast, sprawling areas of the heavens on delicate photographic plates. These thin glass plates were meticulously coated with highly light-sensitive chemicals that reacted silently when exposed to distant starlight focusing through a telescope. After hours of quiet exposure, these plates were carefully developed in the dim, red-lit sanctuary of a darkroom, gradually revealing thousands of tiny, silvered points of light. Each of those minuscule points represented a distant, magnificent object situated somewhere in the endless cosmic ocean. Vibrant stars within our own Milky Way, tightly bound clusters of older stars, glowing nebulae, majestic spiral galaxies far beyond our own, and, occasionally, something truly anomalous and unusual. During the optimistic decades of the 1950s and 1960s, astronomers began paying remarkably close attention to certain peculiar objects that appeared particularly intensely blue on these photographic plates. In the language of astronomy, blue light often signals extremely hot, highly energetic, and violent sources of energy. Young, massive stars, for example, can burn with a brilliant, fierce bluish hue because their outer surfaces are incredibly hot. But some of these strange blue objects catalogued during this exciting era behaved quite differently from ordinary, well-behaved stars. They appeared completely star-like through telescopes, meaning they looked like sharp, individual points of light rather than the fuzzy, extended structures characteristic of distant galaxies. Yet, their light carried deeply mysterious, incomprehensible signatures when analyzed in close detail. One major catalog that diligently recorded many of these puzzling objects was compiled at the historic Tinintler Observatory in Mexico. Astronomers at this observatory were conducting a systematic, sweeping survey of these elusive blue stellar objects, points of light that shone with an unusually brilliant blue quality compared to the countless surrounding stars. Each unique object in the resulting catalog received a simple utilitarian label, TON, followed by a specific designation number. 2618 was merely one of those quiet, unassuming entries. At the time of its cataloging, it did not seem particularly special or significant compared to the many others surrounding it. It was simply one more anonymous blue dot recorded in a vast celestial census. But astronomy was rapidly entering a magnificent new golden era. As delicate spectrographs steadily improved, scientists began dissecting and studying the light from these distant, mysterious objects in far greater, more intimate detail. A spectrograph works by elegantly spreading incoming light into its component, colorful wavelengths, allowing astronomers to read the unique, barcode spectral patterns produced by different chemical elements. When the faint spectrum of T618 was eventually captured and analyzed, the results were deeply puzzling. Instead of the familiar, predictable patterns of lines typically seen in the light of ordinary stars, the radiation from this baffling object exhibited incredibly broad emission lines, brilliant, glowing features produced by extremely hot, highly energetic gas. Even more astonishing to the researchers was just how remarkably wide those lines appeared to be. Broad emission lines strongly indicate that the chaotic gas producing them is moving at extremely high speeds. The swifter and more violently the gas moves, the more its emitted light is stretched and spread out across a wider spectrum of wavelengths. In the case of TON 618, the velocities suggested by these broad lines were nothing short of staggering, revealing colossal gas clouds that appeared to be hurtling through space at several thousands of kilometers/s. Absolutely nothing within the quiet, predictable life cycle of an ordinary, peaceful star could ever generate such cataclysmic motion. Around this very same period, astronomers were just beginning to unravel the mysteries of a strange new class of celestial objects known as quasars. This peculiar term, quasar, originally stood as an abbreviation for a quasi-stellar radio source. Early, rudimentary radio telescopes had detected incredibly powerful, unseen radio emissions emanating from points in the night sky that, to optical telescopes, looked like nothing more than common, faint stars. At first, these perplexing discoveries deeply confused the scientific community. How could an object that appeared so deceptively like a simple, solitary star produce such an overwhelming torrent of radio energy? The profound mystery finally began to unravel when curious astronomers painstakingly studied the spectra of these enigmatic objects and realized, with great awe, that they were not stars at all. Instead, they were incredibly distant, ancient galaxies whose brilliant central regions were producing unimaginable, colossal amounts of energy. The monstrous engine driving these quasars turned out to be supermassive black holes, aggressively feeding on the surrounding cosmic matter that fell hopelessly into their inescapable grasp. Once this revolutionary theory became widely accepted, astronomers eagerly began re-examining many of the strange, faint blue objects that had been catalogued decades earlier. 2618 quickly attracted intense attention. Its analyzed spectrum clearly exhibited the unmistakable, characteristic signatures of a quasar, showcasing extremely bright emission lines birthed by superheated gas swirling near an overwhelmingly powerful central energy source. But there was another vitally important clue hidden deep within the subtleties of its spectrum. The wavelengths of the traveling light were shifted dramatically and profoundly toward the far red end of the spectrum. This remarkable cosmic phenomenon, known as red shift, occurs because our universe is continuously expanding. As ancient light journeys across vast, unfathomable cosmic distances, the very stretching of space itself elongates the wavelengths of that traveling light, making them appear significantly redder to our eyes than they originally were when they began their journey. Naturally, the greater this measured red shift, the farther the ancient object lies from our home on Earth. When astronomers carefully measured the dramatic red shift of T618, they discovered something truly remarkable and humbling. The object was located at an incredibly distant frontier, more than 10 billion light-years away from us. This means that the ancient light reaching our telescopes today actually began its epic journey long before our own solar system had completed even half of its single grand orbit around the Milky Way galaxy. In other words, the starlight we gaze upon now left to 618 when the universe itself was in its vibrant youth, much younger than it is today. At such staggering, unfathomable distances, any object must be peerlessly, extremely luminous to remain visible to our instruments at all. And 2618 was indeed extraordinarily, blindingly bright. When astronomers mathematically calculated its absolute luminosity, the sheer total energy it continuously emits, they realized with astonishment that it was shining with the brilliant power of hundreds of trillions of suns combined. Absolutely no single star in existence could ever produce such a devastating amount of energy. The only plausible explanation consistent with these groundbreaking observations was the presence of a colossal, massive black hole surrounded by a rapidly feeding, glowing accretion disk. The doomed gas spiraling inward would heat up to millions of tempestuous degrees, releasing absolutely tremendous, violent amounts of radiation. This brilliant radiation would then travel tirelessly across billions of light-years, eventually kissing the lenses of telescopes on Earth. But the sheer, blinding brightness of the quasar was merely the beginning of the wonder. As our measurement techniques steadily improved, scientists began estimating the titanic mass of the unseen black hole responsible for generating this incredible, fierce energy. Using the precise techniques we discussed earlier, meticulously studying the rapid motion of swirling gas within the broadline region and applying the fundamental, immutable laws of gravity, astronomers ultimately arrived at a stunning, almost unbelievable conclusion. The central black hole must contain tens of billions of solar masses within its dark core. That staggering estimate firmly placed TUN 618 among the absolute most massive black holes ever discovered by humanity. And yet, despite its unbelievably enormous, monstrous scale, it remains completely, utterly invisible to the naked eye and lens. Even our most powerful, advanced telescopes cannot resolve the physical structure of the black hole itself. From our vantage point on Earth, the entire grand system still appears as nothing more than a single, lonely, distant point of faint light. But that quiet, faint point of light represents one of the most hostile, extreme environments in the entire known universe. Gas racing at incredible speeds, temperatures rising relentlessly to millions of degrees, unleashing a torrent of radiation so fiercely powerful that it completely outshines the vast host galaxy itself. And at the absolute, silent center of this cosmic tempest lies an event horizon of such colossal proportions that it would effortlessly swallow our entire solar system many times over. The profound discovery of T618 beautifully illustrates a fascinating truth about the nature of astronomy. Sometimes, the most extraordinary cosmic wonders begin as mere whisper-quiet entries in a dusty catalog. A tiny, almost imperceptible smudge on a photographic plate, or a simple sterile number assigned during a routine sky survey. Only much later, through painstaking, meticulous measurement and patient, devoted analysis, does the true, awe-inspiring nature of the object finally reveal itself. In this remarkable case, a seemingly faint, delicate blue point of light turned out to be the luminous signature of one of the most colossal black holes ever known to exist. Yet, even now, N618 remains far beyond our direct human reach, residing billions of light-years away in the deepest, most ancient corners of the universe. The very light we gaze upon today began its lonely journey toward us during a primordial epoch when the first galaxies were still gently assembling. Yet, despite this unfathomable distance, its astonishing, radiant brightness allows us to study its secrets in surprisingly vivid detail. Pause for a moment to truly contemplate the staggering amount of light produced by an entire galaxy. A grand galaxy like our own majestic Milky Way harbors hundreds of billions of individual stars. Each and every one of those stars continuously releases immense energy in the form of brilliant light and searing heat, steadily burning its nuclear fuel deep within its core. Some stars are modest, small, and faint, whispering their light into the dark. Others are gargantuan and dazzlingly bright, radiating thousands or even millions of times more intense energy than our own modest sun. When all of those billions of stars shine in unison, their combined, harmonious glow weaves the soft, luminous band of light that arches across our night sky, the familiar path we lovingly recognize as the Milky Way. From our humble vantage point nestled deep within its spiral arms, that collective glow appears to us as a serene, gentle river of starlight softly flowing across the silent darkness. Yet, if you were to stand far outside the boundaries of the Milky Way, gazing back toward it from the deep void, our galaxy would reveal itself as a breathtaking, luminous spiral island suspended in the cosmos, shimmering with the collective brilliance of billions upon billions of radiant suns. Such a colossal quantity of light is nearly impossible for the human mind to fully comprehend. But here lies the truly astonishing revelation. The dazzling quasar surrounding 618 can easily outshine an entire galaxy of that scale. A single, relatively compact region surrounding this supermassive black hole can unleash far more raw energy than the combined light output of hundreds of billions of stars. When astronomers first came to realize this staggering truth, it seemed almost utterly unbelievable. For generations, galaxies themselves were confidently believed to be the grandest, most luminous structures in the cosmic tapestry. Their vast, majestic kingdoms of stars, swirling gas clouds, and softly glowing nebulae seemed entirely unmatched in both physical scale and sheer brilliance. The revolutionary concept that a single, compact point in space could rival or even vastly exceed that collective cosmic glory felt completely counterintuitive, defying all established intuition. And yet, that is precisely the miraculous feat that these quasars perform. To truly comprehend how this is possible, it is helpful to contemplate the profound difference between the way stars generate their light and the way chaotic matter behaves in the extreme vicinity of a black hole. Stars shine through the elegant process of nuclear fusion. Deep within the crushing core of a star, simple hydrogen atoms are squeezed tightly together under unimaginably immense pressure and soaring temperatures. These atoms forcefully fuse into helium, releasing a burst of pure energy in the process. That liberated energy then begins a slow, epic journey outward through the dense, glowing layers of the star, until it finally breaks free into the void as visible light. This stellar fusion is incredibly powerful, especially when compared to mundane chemical reactions like the simple burning of wood or fossil fuels. Yet, as mighty as fusion is, it is still not the most efficient mechanism the universe possesses for converting raw matter into brilliant energy. Black holes introduce a fundamentally different, far more violent process. When interstellar gas falls helplessly toward a black hole, it does not instantly vanish beyond the shadowy threshold of the event horizon. Instead, it gathers into a colossal, rapidly swirling structure known as an accretion disk. Within this cosmic whirlpool, intense gravity relentlessly pulls the gas inward, while the ferocious friction between colliding particles causes the material to heat up to an unimaginable degree. As the doomed gas spirals ever closer to the abyss of the black hole, it accelerates to mind-boggling, terrifying speeds. A significant portion of this swirling matter begins moving at a substantial fraction of the speed of light itself. Under these incredibly extreme, turbulent conditions, raw gravitational energy is converted directly into searing heat and brilliant radiation with a truly remarkable, unmatched efficiency. In fact, matter, falling into a swirling accretion disk surrounding a black hole, can convert up to an astonishing 10% of its total mass directly into pure, radiant energy. While this may not sound particularly dramatic at first glance, it is astonishingly, almost unimaginably efficient when compared with the ordinary process of nuclear fusion. The thermonuclear fusion that patiently powers the stars converts less than a mere 1% of their original mass into energy. Consequently, the majestic process powering quasars can be more than 10 times as efficient as the stellar engines that light up the night sky. This profound difference explains precisely why the chaotic regions surrounding supermassive black holes can shine with such dazzling, peerless brilliance. When truly colossal reservoirs of cosmic gas spiral downward toward the gargantuan black hole at the heart of a quasar, the resulting release of energy becomes utterly staggering. The quasar surrounding TON 618 stands as one of the most extreme and awe-inspiring examples known to modern science. Astronomers carefully estimate that it produces a magnificent luminosity equivalent to hundreds of trillions of our own suns. To put this grand scale into perspective, the entire Milky Way galaxy shines with a collective luminosity roughly equal to only about 100 billion suns. This means that the mighty quasar powered by TON 618 can be several thousands of times brighter than our entire home galaxy. Yet, when viewed from the quiet shores of Earth, this incredibly fierce energy appears merely as a faint, unassuming dot in the night sky. The vastness of cosmic distance has a profound way of shrinking even the most luminous giants into tiny, delicate points of light. TON 618 lies situated more than 10 billion light-years away from us. Over the course of that immense and lonely journey, the ancient light from the quasar steadily spreads out in every conceivable direction across the vast, expanding universe. By the time it finally reaches Earth, only a minuscule fraction of that ancient radiation manages to enter our sensitive telescopes. Still, despite the journey, the quasar remains sufficiently bright to be studied by astronomers in truly remarkable detail. When astronomers carefully analyze the delicate spectrum of its captured light, they clearly observe the distinct signatures of gas moving at absolutely extraordinary speeds. Violent clouds of interstellar material orbiting close to the black hole reach dizzying velocities of several thousand kilometers per second. These rapid, chaotic motions dramatically broaden the emission lines in its spectrum, providing invaluable clues about the turbulent environment surrounding the central object. Furthermore, the sheer brightness of the quasar also reveals the immense volume of matter that must be continuously falling into the insatiable black hole. To maintain such a colossal and luminous output, the swirling accretion disk must be perpetually supplied with enormous, sweeping quantities of cosmic gas. Vast, cascading streams of interstellar material likely flow toward the gravitational center of the host galaxy, constantly feeding the black hole and sustaining the quasar's immense energy production. This relentless feeding process may continue undisturbed for millions of years. During this immense epoch, the quasar reigns as one of the most dominant and influential sources of radiation in its surrounding region of space. In fact, the staggering energy released by these quasars can profoundly influence the long-term evolution of their entire host galaxies. The intense, Burning radiation and powerful galactic winds generated near the black hole can forcefully push pristine gas far away from the galactic center. These sweeping outflows may actively regulate how quickly new stars can form, thereby shaping the long-term destiny and development of the galaxy itself. In this beautiful yet violent way, a black hole that occupies only a tiny, localized region at the center of a galaxy can still profoundly affect cosmic structures spanning tens of thousands of light-years. TUN 618 vividly demonstrates this extraordinary relationship at a particularly extreme and terrifying scale. Its truly enormous mass allows it to generate one of the most brilliantly luminous quasars ever observed in cosmic history. The vibrant accretion disk surrounding the black hole glows with an almost unimaginable intensity, while powerful jets and winds may carry energetic radiation far beyond the central galactic region. Yet, despite all this spectacular activity, the black hole itself remains forever hidden in total darkness. No human telescope can ever hope to see the silent event horizon directly at such unimaginable cosmic distances. Instead, astronomers must patiently observe the bright, glowing structures surrounding it. The radiant, swirling disk of gas, the fast-moving clouds of matter producing broad emission lines, and the highly energetic radiation escaping out into the coldness of intergalactic space. All of these celestial features combine to form what we recognize today as a majestic quasar. One deeply fascinating aspect of quasars is that they were far more common in the chaotic infancy of the early universe than they are in the cosmos today. When we gaze upon objects like TUN 618, we are peerlessly looking billions of years back into the ancient past. During that distant primordial era, infant galaxies were vastly younger, cradling immense, untouched reservoirs of cosmic gas within their swirling hearts. Violent yet majestic collisions between these crowded galaxies occurred with far greater frequency, relentlessly funneling massive streams of additional material directly toward their dark, hungry centers. These chaotic cosmic conditions provided an incredibly abundant feast of fuel for rapidly growing black holes. As colossal torrents of gas poured ceaselessly into the deep central regions of galaxies, these black holes grew at an astonishing pace, powering the birth of extremely bright, dazzling quasars. Over vast epochs of time, however, many galaxies gradually depleted much of their available gas, or forcefully expelled it far into the void through fiercely energetic outflows. As this vital fuel supply slowly diminished, those brilliant quasars gradually faded into quiet darkness. Today, in our mature universe, most supermassive black holes appear relatively quiet and dormant. The sleeping black hole nesting at the very center of our own Milky Way, for example, is currently inactive and peaceful compared to those ancient, powerful quasars. Although it still occasionally consumes minuscule amounts of drifting gas or dust, it does not produce the kind of overwhelmingly intense, blinding radiation seen in monstrous cosmic objects like 2618. This profound difference beautifully highlights a fascinating transient phase in the grand life cycle of galaxies. There exist epic periods when a central black hole awakens to become extremely, violently active, shining brilliantly as a dominant quasar for millions of fleeting years. Later, the chaotic activity gently subsides, and the host galaxy settles down into a much quieter, more serene state. The magnificent T618 represents one of those rare, highly active phases, captured at an absolutely extraordinary level of cosmic brightness. Because this spectacular quasar is so incredibly luminous, its brilliant presence can be detected even across the most enormous, unimaginable cosmic distances. Patient telescopes on Earth capture its ancient, weary light only after a staggering journey lasting more than 10 billion years through the dark void. In a deeply profound sense, observing the distant TUN 618 allows modern astronomers to look directly back into a much earlier, wilder chapter of our universe. At that remote time, primordial black holes were growing rapidly, and colossal quasars brightly illuminated the young, developing cosmos with their intense, piercing radiation. The lonely light from TUN 618 has been tirelessly traveling through an ever-expanding space for the vast majority of cosmic history before finally, gently reaching our sensitive instruments. Yet, incredibly, all of that radiant light originates solely from the chaotic region closely surrounding a black hole whose true, ultimate boundary the event horizon, remains forever hidden from our prying view. The immense brightness of the quasar guides us to detect the object, but it stubbornly refuses to reveal the exact, mysterious size of the black hole itself. Imagine, if you will, a solemn boundary in space that absolutely cannot be crossed in reverse. This is not because there stands a physical wall or a cold, solid surface, but rather because the fundamental laws of physics themselves strictly prevent anything from ever returning once that fateful boundary is passed. No advanced spacecraft, however powerful, could hope to escape. No desperate signal could ever travel back outward to tell the tale. Even light itself, which normally sweeps faster than anything else in the vast universe, would utterly fail to break free from this relentless grasp. That invisible, absolute boundary is what astronomers softly call the event horizon. It marks the terrifying point where gravity becomes so overwhelmingly strong that every single possible path ahead leads inexorably inward. Outside this event horizon, celestial objects can still drift and move freely through the surrounding space. They may gracefully orbit the black hole, lazily drift away, or even escape its pull entirely if they travel fast enough. But the moment that silent event horizon is crossed, every single future direction points deeper and deeper toward the crushing center. For many, the evocative phrase black hole instantly brings to mind a terrifying image of a chaotic cosmic vacuum cleaner, violently and blindly pulling everything inward from impossibly great distances. The reality, however, is far more subtle and elegant. A black hole behaves much like any other massive, peaceful cosmic body when you are safely far away from it. Entire planets could calmly orbit a black hole just as they orbit a warm, life-giving star, provided they remained comfortably outside that critical event horizon. The true, stark difference appears only at that whisper-thin, invisible boundary. The event horizon alone defines the true physical size of a black hole, not the swirling, glowing accretion disk surrounding it, and not the bright, energetic jets that may dramatically erupt from nearby agitated gas. Those are merely spectacular, external features, but they are absolutely not the black hole itself. The black hole, in its purest essence, is defined solely by that quiet region where escape becomes completely, irrevocably impossible. For smaller, less monstrous black holes, this fateful boundary can be surprisingly, almost shockingly compact. If our own warm sun were suddenly replaced by a quiet black hole of the exact same mass, its event horizon would measure a mere 3 kilometers in radius. That means the entire mass of the sun, representing more than 300,000 Earths, would be incredibly compressed into a dense, silent sphere smaller than many modest towns. From a safe distance, however, the ghostly gravitational pull would remain completely identical to that of our familiar sun. Our blue Earth could continue orbiting exactly as it does now, undisturbed by the darkness at the center. The terrifying difference would only manifest if some wandering object drifted too close to the silent event horizon. Beyond that invisible threshold, there would be absolutely no turning back. As the immense mass of a black hole steadily increases, the dark radius of its event horizon grows proportionally. Every single additional solar mass adds roughly 3 kilometers to this shadowy radius. This elegant relationship, first described by the physicist Carl Schwarz in the year 1916, beautifully allows astronomers to estimate the actual physical size of a black hole once its mass is known. The fundamental formula is remarkably simple. For every mass equal to our sun, the event horizon expands outward into the void by roughly 3 kilometers. When we courageously apply that rule to extremely massive black holes, the scale becomes utterly astonishing. Consider, for instance, the slumbering black hole at the center of our galaxy Sagittarius A star. With a colossal mass of about 4 million suns, its event horizon extends roughly 12 million kilometers in radius. That already sounds unbelievably enormous to our human minds. After all, the entire physical diameter of our sun is only about 1.4 million kilometers. Thus, the silent event horizon of Sagittarius A star is several times larger than the glowing sun itself. Yet, on the grandest cosmic scales, that still counts as relatively modest, a mere speck compared with the true giants found in some distant ancient galaxies. The mythical Titan Tun 618 belongs to an entirely different, terrifying category altogether. Earlier we discussed how astronomers carefully estimate that the titanic black hole powering tons 618 contains around 66 billion solar masses. When the simple Schwartz relationship is applied to that colossal mass, the physical size of the event horizon expands to a truly staggering distance. The radius reaches roughly 195 billion kilometers. That immense number can be exceedingly difficult to interpret on its own, so astronomers often compare it with the familiar, comforting structures of our own solar system. For example, the life-bearing orbit of Earth lies about 150 million kilometers from the Sun. The grand orbit of Jupiter stretches roughly 780 million kilometers outward. Neptune, the most distant major planet in our system, slowly travels around the Sun at an average distance of about 4.5 billion kilometers. Those vast distances already feel overwhelmingly enormous to us. Human spacecraft launched from Earth can take painful years to reach Jupiter, and more than a weary decade to finally reach the outer planets. Yet, the quiet event horizon of T618 would extend far, far beyond all of those distant orbits combined. Even frozen Neptune would lie helplessly deep inside that dark boundary where escape becomes utterly impossible. If this gargantuan black hole somehow replaced our Sun at the center of the solar system, most of our familiar planets would already find themselves trapped inside the event horizon. Only the farthest, lonely, icy objects in the outermost regions might barely remain outside that dreadful, invisible surface. This startling comparison reveals something profoundly important. The event horizon of Ton 618 is not just incredibly large compared with ordinary planets or stars. It is vast compared with the entire sweeping architecture of a planetary system. And that inevitably leads to a deeply curious realization. For black holes of this magnificent scale, the boundary itself begins to feel less like a localized, compact object and far more like an enormous, sovereign region of space. Imagine, if you will, drifting slowly and silently toward such a black hole from the deep safety of far away. At first, absolutely nothing unusual would appear. The black hole itself would remain completely invisible, perpetually hidden behind the absolute, velvet darkness of its event horizon. The brilliantly glowing accretion disk might be visible nearby, radiating enormous, blinding amounts of energy as superheated gas spirals helplessly inward. But the event horizon itself would not look like a solid sphere floating in space. Instead, it would merely appear as a dark, silent region where the distant background stars begin to mysteriously distort. The immense, crushing gravity near the black hole powerfully bends the paths of passing light rays, creating a dramatic, swirling gravitational lensing effect. Stars shining far behind the black hole would appear warped and stretched into delicate, glowing arcs of ghostly light. As you approached closer and closer to this cosmic abyss, time itself would begin to behave quite differently. According to the elegant theory of general relativity developed so long ago by Albert Einstein, immensely strong gravitational fields slow the passage of time itself. Clocks nestled near the fierce, invisible grip of a black hole tick with an agonizing slowness compared to those drifting peacefully in the quiet, distant reaches of space. To a silent observer watching safely from a comfortable distance, your intrepid spacecraft would appear to decelerate in slow motion as it drew closer to the edge of the event horizon. The desperate light signals sent from your vessel would stretch lazily toward longer, redder wavelengths, gradually fading like dying embers until they vanished entirely into the dark void. From the solemn perspective of that faraway onlooker, your spacecraft would seem to freeze, suspended forever as an eternal ghost at the very boundary of the event horizon. Yet inside the ship, your personal experience would unfold quite differently. You would continue to drift forward without pause, feeling perfectly normal. Your onboard clocks would tick away with reassuring familiarity. Absolutely nothing unusual would mark the exact, fateful moment you crossed the threshold of the event horizon itself. That monumental transition would remain profoundly silent and entirely invisible. Once inside, however, the laws of the universe bend, and your forward path would lead inevitably, relentlessly toward the dark, crushing heart of the black hole. Yet, the truly remarkable thing about gargantuan cosmic giants like TON 618 is that the tidal forces acting near their event horizons can be surprisingly, almost mercifully gentle. For smaller, stellar mass black holes, These gravitational tidal forces escalate so violently near the threshold that any physical object is dramatically, painfully stretched long before it even arrives. This terrifying stretching effect, colorfully termed spaghettification, would ruthlessly tear apart any brave explorer or vessel venturing too close. But for these rare, ultramassive black holes, the event horizon lies at such an immense, unfathomable distance from the central singularity that the difference in gravitational pull between the front and back of an object becomes incredibly, imperceptibly small at that outer boundary. In theory, a spacecraft crossing the threshold of TON 618 might not experience any violent, destructive stretching right away. The gravitational gradient at such a vast, sweeping distance from the core would remain comparatively mild. Of course, continuing your journey deeper inside the black hole would still inexorably carry you toward a final, crushing region where gravity grows overwhelmingly absolute. Yet, the sheer scale of this colossal event horizon completely alters the poetic nature of the voyage. Instead of plunging instantly into a chaotic maelstrom of destruction, an incoming object might glide across the invisible boundary without noticing anything unusual at the exact, fleeting moment it occurs. This surreal property beautifully highlights how sheer scale fundamentally transforms our human understanding of these cosmic abysses. For smaller black holes, the event horizon acts as a sharply hostile, lethal zone where tidal forces rapidly escalate to extremes. For ultramassive titans, the boundary swells into an enormous, surprisingly tranquil arena, at least locally. Yet, this serene calmness only masks the deeper, chilling reality that no escape remains possible once that line is crossed. Beyond it, all paths through the tapestry of spacetime inevitably curve inward. To those observers watching safely from the outside world, the interior of the event horizon remains forever, tantalizingly out of reach. Signals sent from beyond that veil can never return, meaning the inner secrets are eternally hidden from the rest of the universe. Yet, even without peering inside, astronomers can still elegantly calculate the physical size of that invisible boundary simply by measuring the immense mass of the black hole itself. And in the breathtaking case of TON 618, those cosmic measurements reveal something truly extraordinary. The event horizon alone spans a vast, majestic region wider than many entire planetary systems. Consider, for a quiet moment, the sprawling layout of our own solar system. Even though most textbook diagrams depict our neighboring planets neatly lined up close together, the true physical distances separating them are utterly enormous. The vast space inside our immediate planetary neighborhood is, in truth, mostly empty silence. Our warm sun sits serenely at the center, shining with steady brilliance, while the planets faithfully travel along their wide, elegant paths that stretch for billions of kilometers across the dark void. From our vantage point on Earth, these colossal distances can easily feel abstract and surreal. The raw numbers are so staggeringly large that they lose all practical meaning unless we patiently imagine them, step by step. Earth, for instance, gracefully orbits the Sun at an average distance of roughly 150 million kilometers. Astronomers elegantly refer to this distance as 1 astronomical unit, often shortened to a simple 1 AU. It serves as a convenient, poetic measuring stick for mapping the vast distances within our solar neighborhood. Mercury, the closest and swiftest planet to the Sun, travels at roughly 0.39 astronomical units. Venus, shrouded in its thick veil of mystery, moves gracefully along a path at about 0.72 astronomical units. Beyond her, the crimson world of Mars follows its silent, solitary orbit around 1.5 astronomical units away from the Sun. These vast distances already feel immense by our everyday standards, but the majestic outer planets push the scale of our imagination much farther. Jupiter, the grandest planet in our solar system, orbits at about 5.2 astronomical units. Saturn lies adorned in its magnificent rings around 9.5 astronomical units from the Sun. Uranus travels through the cold dark at roughly 19 astronomical units, and Neptune, the outermost major planet of deep blue, circles the Sun at about 30 astronomical units. Even at that incredible distance, the Sun's silent gravity still completely dominates the motion of all these celestial objects in the solar system. Beyond the orbit of Neptune lies the Kuiper Belt, a wide, mysterious region filled with countless icy bodies and quiet dwarf planets. Farther still into the dark abyss is the distant Oort cloud, a vast, majestic spherical halo of comets that may extend tens of thousands of astronomical units from the Sun. When we picture our solar system in this grand way, it becomes beautifully clear that our planetary neighborhood is already incredibly, breathtakingly large. And yet, the unimaginable event horizon of to 618 would extend across a truly surprising and humbling portion of that very space. Earlier, we discussed how astronomers estimate the unfathomable size of this supermassive black hole using the precise relationship between mass and radius first described by Carl Schwarz. With an estimated colossal mass of about 66 billion suns, the resulting event horizon reaches roughly 195 billion kilometers in radius. That staggering figure translates to about 1,300 astronomical units across in diameter. Numbers of this magnitude can still feel entirely distant from our everyday human experience, so astronomers often compare them directly with the familiar orbits of our own planets. Let us imagine placing to 618 at the very center of our solar system, exactly where the Sun currently sits in its warm glory. At first glance, nothing would look very different from far, far away. The black hole itself would remain completely invisible, forever hidden behind the dark veil of its event horizon. The surrounding space would appear profoundly dark, except for any glowing, superheated material spiraling wildly around its edge. But as we begin marking the positions of our familiar planets relative to that dark event horizon, the true scale becomes terrifyingly clear. Mercury, which orbits only 58 million kilometers from the Sun, would disappear instantly and silently inside the eternal boundary. Venus, too, would lie deep within the shadow of the event horizon. Earth's own orbit at 150 million kilometers would not even come close to the edge. Our home planet would already be nestled far inside the dark region where escape is absolutely impossible. Mars, which circles the Sun at about 228 million kilometers, would inevitably share the exact same fate. In fact, the colossal event horizon of TON 618 would extend far beyond the entire inner solar system. Jupiter's grand orbit at roughly 780 million kilometers would also lie well within the dark, silent boundary. Saturn, Uranus, and Neptune, planets we usually think of as existing in the extremely distant, cold reaches of space, would still be effortlessly swallowed by the event horizon. To put this another way, the immense diameter of this event horizon is easily large enough to contain the orbits of every major planet in our solar system. Only the most distant, frozen regions of the Kuiper Belt would remain outside. Even then, the dark boundary would still stretch outward through a massive portion of the space where icy dwarf planets and lonely comets travel. For an observer watching from far beyond the edges of our solar system, the event horizon would appear as a vast, invisible sphere of absolute darkness, engulfing nearly the entire planetary system. And yet, despite its truly enormous, terrifying size, the giant black hole would not behave like a chaotic cosmic vacuum cleaner, pulling everything inward instantly. Gravity still follows the same beautifully predictable rules. Objects situated safely outside the event horizon could orbit the black hole just as planets orbit our Sun today. If Earth somehow remained outside that dark boundary, perhaps placed far enough away in the quiet void, it could continue orbiting normally. The stark difference would appear only when an unsuspecting object drifted just a little too close to the event horizon. Cross that invisible final boundary, and absolutely no escape would be possible. This comparison reveals something truly remarkable about the majestic scale of TON 618. Black holes are so often imagined as compact, almost point-like objects, extremely small regions where vast amounts of matter have been tightly squeezed into a state of unimaginable density. That familiar description works remarkably well for stellar black holes, those stellar remnants created when massive stars collapse under their own crushing gravity. But ultramassive black holes operate on a completely different, almost incomprehensible scale. For TON 618, the dark boundary of the event horizon alone covers a vast region wider than many entire planetary systems. And yet, this terrifying event horizon is merely the beginning. The immense gravitational influence of such a black hole extends far, far beyond its physical boundary. Vast, swirling gas clouds orbiting nearby can form colossal, glowing accretion disks that span distances many times larger than the event horizon itself. Within the hearts of powerful quasars, these radiant disks glow with an almost blinding brightness as trapped matter spirals helplessly inward, heating up to millions of scorching degrees. The monumental accretion disk surrounding TON 618 likely stretches across vast regions comparable to the entire size of our solar system, or perhaps even larger. Fierce, energetic jets of high-energy particles may also erupt violently from the spinning poles of the disk, blasting intense radiation across the silent voids of intergalactic space. All of this chaotic, highly energetic activity occurs within the inescapable gravitational reach of the central black hole. When dedicated astronomers observe such distant systems from the quiet observatories of Earth, they often cannot resolve these individual, intricate structures because of the truly immense, mind-boggling distances involved. Instead, they must carefully analyze the collective light coming from the quasar as a single, unified whole. From that ancient light, they brilliantly infer the swirling speeds of the distant gas clouds, the extreme temperatures of the glowing accretion disk, and the colossal mass of the hidden black hole driving this entire cosmic process. Even though the black hole itself remains completely invisible, cloaked in absolute darkness, its powerful, undeniable influence reveals its grand presence. This striking comparison with our own familiar solar system also highlights something deeply curious about the nature of scale in our universe. From our humble perspective here on Earth, our solar system feels absolutely enormous. The silent distance from our warm sun to the icy, remote planet Neptune is more than 30 times the distance from the Earth to the Sun. Human spacecraft, traveling at breathless speeds of tens of thousands of kilometers per hour, must take long, lonely years just to cross that vast distance. And yet, the event horizon of TON 618 alone stretches far, far beyond that entire cosmic region. Facing this kind of scale forces us to completely rethink what the word large really means. In our brief everyday lives, we measure our world in modest meters or kilometers. In astronomy, however, we quickly find ourselves moving into millions, billions, and even trillions of kilometers. Even then, the largest, most majestic objects in the universe often exceed those massive measurements by truly enormous, unfathomable margins. TON 618 sits proudly near the extreme, absolute end of that cosmic scale. Its dark event horizon could easily swallow the entire structure of our solar system with room to spare. And yet, despite this truly incredible, terrifying size, it remains a single, individual object. One singular black hole, one sharp gravitational boundary, one colossal engine powering a brilliant quasar bright enough to be clearly seen across billions of light-years of empty space. Somewhere deep within the dusty, crowded center of our own Milky Way galaxy sits a quiet black hole that astronomers have been passionately studying for decades. It remains permanently hidden behind enormous, thick clouds of interstellar gas and cosmic dust, situated far beyond the physical reach of any spacecraft we could dream of sending today. Even our most powerful, sophisticated telescopes cannot view it directly using ordinary visible light. Yet, its gravitational presence is absolutely unmistakable because the stars in its immediate vicinity move in a very peculiar, highly particular way. That mysterious object is known to us as Sagittarius A star. For many dedicated years, astronomers have carefully and patiently tracked the precise motion of stars orbiting extremely close to this dark, silent region. These nearby stars whip around the invisible, heavy center at truly incredible speeds, completing full, dramatic orbits in only a few Earth years. By measuring those rapid orbits with extreme precision, scientists were eventually able to calculate exactly how much mass must be concentrated in that seemingly tiny cosmic space. The definitive answer turned out to be utterly remarkable. Sagittarius, a star, contains roughly 4 million times the mass of our own Sun. At first hearing, that unimaginable number sounds profoundly enormous. The idea of 4 million suns compressed into a cosmic region smaller than the orbit of Mercury is already a dramatic, breathtaking example of just how strange and counterintuitive black holes can truly be. In fact, this pivotal discovery helped confirm that most large, sprawling galaxies contain supermassive black holes at their very centers. Our own home galaxy is not unusual in this cosmic respect. The Milky Way simply happens to be the one nearby galaxy we can observe and study most closely. Because Sagittarius A star is relatively nearby in vast cosmic terms, situated about 26,000 light-years away, astronomers have fortunately been able to observe the intricate motion of individual stars dancing around it. Those distant stars act almost like delicate test particles, silently tracing the invisible shape of the massive gravitational field. Their graceful paths clearly reveal the immense mass hidden secretly at the center. One particular star, known to us as S2, travels on an extremely elongated and eccentric orbit that carries it breathtakingly close to the black hole once every 16 years. During this closest approach, the star hurtles through space at astonishing speeds of thousands of kilometers per second. The unimaginable gravity required to produce such frantic motion can only ever come from a supermassive black hole. In 2020, the extraordinarily careful and precise measurements of these stellar orbits earned the prestigious Nobel Prize in Physics for the dedicated scientists who passionately led the research. But even though Sagittarius A star is profoundly impressive, it becomes something of a modest, humble example once we compare it with the colossal giant powering Ton 618. Earlier we mentioned that Ton 618 contains roughly 66 billion solar masses. When placed side by side with the 4 million solar masses of our own central black hole, the sheer difference becomes absolutely staggering. Ton 618 easily outweighs the silent black hole in our galaxy by more than a spectacular 16,000 times. Numbers of such immense size can easily lose their meaning unless we pause thoughtfully and translate them into something far more concrete. One helpful way to think about this incredible comparison is to consider the physical size of the event horizon. The event horizon of Sagittarius A star has a radius of about 12 million kilometers. That means the entire dark boundary of the black hole spans roughly 24 million kilometers across. Although that sounds enormous, it is actually significantly smaller than the orbit of Mercury around our Sun. Mercury travels about 58 million kilometers from the Sun. So if Sagittarius A star replaced the Sun at the center of our solar system, the event horizon would sit comfortably well inside Mercury's orbit. The remaining planets could happily continue orbiting quite normally from a perfectly safe distance. Now, however, imagine placing the monstrous Ton 618 in that very same central position. Instead of a modest boundary 24 million kilometers wide, its gargantuan event horizon would stretch across nearly 390 billion kilometers. That immense distance reaches far beyond the lonely orbit of Neptune and deep into the cold, outer regions of the solar system. So the profound difference between the two black holes is not just large. It represents an entirely different cosmic scale. If Sagittarius A star were a simple, small coin placed on a table, Ton 618 would be more like an enormous, towering stadium surrounding it. This vivid comparison helps explain why astronomers sometimes refer to titanic objects like T 618 as ultramassive black holes. They go far beyond the already impressive scale of typical supermassive black holes. Yet physical size is by no means the only difference between the two. Their surrounding environments also behave in very different, contrasting ways. Sagittarius A star is currently quiet and dormant. Although small, wispy amounts of gas occasionally drift lazily toward it, the sleeping black hole at the center of the Milky Way is not actively consuming large, voracious quantities of matter. Because of that peaceful nature, it produces relatively little radiation compared with a brilliant, bright quasar seen in distant galaxies. If we could observe Sagittarius Earth star from far away, it might appear almost completely invisible against the luminous background of stars. Ton 618, by stark and dramatic contrast, is surrounded by one of the most luminous quasars ever observed in the universe. Vast streams of gas falling helplessly toward the black hole form an enormous, swirling accretion disk that glows intensely as it violently heats up. This friction-heated disk radiates truly tremendous amounts of energy across the entire electromagnetic spectrum, including visible light, ultraviolet radiation, and high-energy X-rays. The sheer energy output is so incredibly large that the brilliant quasar easily outshines the entire galaxy that hosts it. In other words, the black hole in our own galaxy is currently resting in quiet slumber, while the one inside Ton 618 is actively and hungrily feeding. This continuous feeding process dramatically and spectacularly increases the brightness of the surrounding cosmic region, casting a brilliant shroud of light that allows patient astronomers to study this ancient system, even though it lies untold billions of light-years away. Without this blazing quasar, the enigmatic to 618 might have forever remained completely invisible to human eyes. Another deeply fascinating difference lies in the delicate way we detect each of these cosmic titans. Sagittarius, a star reveals its ghostly presence through the silent, orbital motion of nearby stars. Because this celestial neighbor is relatively close to us, our modern telescopes can clearly resolve individual stars dancing around its unseen heart. T618, however, dwells far too distant in the cosmic deep for that kind of detailed, intimate observation. Instead, astronomers must carefully analyze the ancient light streaming from the brilliant quasar and measure the rapid motion of glowing gas clouds swirling near the black hole. These turbulent gas clouds produce broad emission lines across the spectrum, and their colossal speeds allow dedicated scientists to estimate the staggering mass of the invisible giant resting at the center.